Betelgeuse is lying to us. For more than a century, we've stared at one of the brightest stars in the night sky and assumed we understood what we were looking at. A dying red supergiant, a stellar bomb counting down to zero. A familiar shoulder in the constellation Orion that any child with a clear night and a pointed finger could find. And then, in late 2019, it started to vanish. Not slowly, not predictably. Betelgeuse dimmed by more than half in a matter of weeks, dropping to the faintest magnitude ever recorded in modern astronomy. The world held its breath. Astronomers scrambled. Every telescope on Earth that could see it turned and watched, waiting for the flash that would mark one of the most violent events the universe can produce, a supernova. The explosion of a star 15 times more massive than our Sun, close enough that for weeks it would outshine the Moon and be visible in broad daylight. But the explosion never came. The dimming stopped. Betelgeuse recovered. And in the months that followed, scientists began to realize they had been watching the wrong thing entirely. Because hidden inside the chaos of that dimming, buried in the data nobody thought to check, was something no one predicted. A second star, a companion, orbiting so deep inside Betelgeuse's own atmosphere that it has been invisible for as long as humans have been looking. Its name is Siwarha, and its existence changes everything, not just what happened in 2019, but how long Betelgeuse has left. Why every prediction about its death has been catastrophically wrong, and what we are actually seeing when we look up at Orion and assume that shoulder will always be there. This is the story of a star that refused to die on schedule, and the secret it kept for 10 million years. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. Betelgeuse has been dying for longer than your species has had language. It has been dying since before the pyramids, before agriculture, before humans figured out how to make fire do anything useful. It has been dying since the last ice age, and it will likely keep dying for another 100,000 years. But in late 2019, for the first time in recorded history, it looked like the wait might finally be over. The star sits in the constellation Orion, marking the hunter's right shoulder. If you have ever looked up at a winter sky in the northern hemisphere, you have seen it, that reddish point of light up and to the left of the three stars forming Orion's belt. Most people never learn its name, but they recognize the shape. Orion is one of the few constellations that actually looks like what it's supposed to represent. Two shoulders, a belt, two legs, and if you squint, a sword hanging from the belt. Betelgeuse is the shoulder, the bright one, the one with the color, except for a few months starting in October 2019, it stopped being bright. Betelgeuse is what astronomers call a red supergiant. That term gets thrown around a lot in popular science articles, usually accompanied by some breathless statement about how, if you dropped this star where our Sun is, its surface would reach past the orbit of Jupiter. Which is true. Betelgeuse is enormous. Its diameter is roughly 700 times wider than the Sun. If the Sun were a golf ball, Betelgeuse would be a small house. Its mass, however, is only about 11 to 15 times that of the Sun. The rest is just atmosphere. A vast, bloated envelope of hydrogen and helium puffed out to ridiculous proportions because the star has run out of fuel in its core and can no longer hold itself together properly. This is what happens when a massive star gets old. It swells. Our Sun will do something similar in about 5 billion years, though it will only make it to red giant status, not supergiant. The Sun does not have enough mass to go supergiant. Betelgeuse does. It started its life with at least 15 to 20 solar masses, burned through its hydrogen in a few million years, which is fast by stellar standards, and then moved on to fusing helium into carbon and oxygen. After that, carbon into neon and magnesium. After that, neon into oxygen and magnesium. Each stage burns faster than the last because each stage releases less energy per fusion reaction, so the core has to burn hotter and faster just to hold up the weight of the layers above it. By the time a star like Betelgeuse gets to fusing silicon into iron, it has maybe a week left, sometimes less. Iron is the end of the line. Fusing iron costs more energy than it releases. The moment a core full of iron tries to fuse, the furnace shuts off. The core collapses. The outer layers, no longer supported, fall inward at a quarter of the speed of light. Then they hit the incompressible core, bounce, and explode outward in a supernova that for a few weeks can outshine an entire galaxy. Betelgeuse has not reached iron yet. It is still somewhere in the middle stages, probably fusing helium or carbon in its core, with shells of lighter elements burning in layers above it like a cosmic onion. But it is close enough to the end that astronomers have spent decades watching it, waiting for the moment it finally lets go. That moment, most scientists agree, is still tens of thousands of years away, maybe 100,000. On a cosmic timescale, that is soon. On a human timescale, it is irrelevant. You will not see it. Your grandchildren will not see it. Your distant descendants, if they are still around and still looking up, might. But in December 2019, it looked like maybe, just maybe, the timeline had moved up. Betelgeuse is a variable star. It pulses. Its brightness changes on a regular cycle, swelling and dimming as the outer layers expand and contract in a slow rhythmic breathing. The main cycle runs about 400 to 430 days, a little over a year. There is also a longer cycle, somewhere around 5 to 6 years, roughly 2200 days, that modulates the shorter one. When both cycles hit their minimum at the same time, Betelgeuse dims noticeably. Astronomers have known this for decades. It is in the textbooks, predictable, boring, in the way that reliable data is boring. In October 2019, the star started dimming faster than the models predicted. By November, it was noticeably fainter. By December, amateur astronomers with backyard telescopes were posting measurements online showing Betelgeuse had dropped from its usual magnitude of about 0.3, which makes it one of the 10 brightest stars in the sky, to around magnitude 1.0, that is roughly half as bright. Still visible, still prominent, but dim enough that people who knew where to look started to notice. By January 2020, it had dropped to magnitude 1.3. That is about 60 to 65% of its normal brightness. The faintest anyone had ever seen it in the modern era of continuous photometric monitoring. Some measurements put it even lower, closer to magnitude 1.6. For a star that has been watched continuously for more than a century, this was unprecedented. And then the speculation started. The first whispers came from the professional astronomy community. Papers started appearing on the preprint server ARISIV suggesting that Betelgeuse might be in the late stages of core collapse. Maybe the core had already started fusing silicon. Maybe the dimming was a sign that the outer envelope was contracting in preparation for the final inward plunge. Maybe we were watching the opening act of a supernova in real time. The idea spread fast. Astronomy blogs picked it up. Science journalists picked it up. Within weeks, mainstream media outlets were running stories with headlines like, "Is Betelgeuse about to explode?" and "Supernova watch. Betelgeuse fading fast." Some of the coverage was careful, hedging with phrases like "could be" and "scientists aren't sure." A lot of it was not. Social media did what social media does. It amplified the most dramatic interpretation and ran with it. Suddenly, everyone with a passing interest in space was talking about Betelgeuse. Reddit threads filled with speculation. Twitter astronomers posted nightly updates on the star's brightness. Amateur observers who had never cared about Betelgeuse before were suddenly pointing their telescopes at Orion every clear night, logging measurements, comparing notes, building light curves. The star had become the most watched object in the sky, and for good reason. If Betelgeuse was really about to explode, it would be the astronomical event of a lifetime, possibly the astronomical event of the millennium. A supernova is not subtle. When a star the size of Betelgeuse goes, it does not fade quietly into the night. It detonates with the energy of 10 to the power of 51 ergs, a number so large it stops meaning anything in human terms. For comparison, the Sun produces about 10 to the power of 44 ergs over its entire 10 billion year lifetime. A supernova releases 100 million times that much energy in a few seconds. Most of that energy goes into neutrinos, ghostly particles that zip through matter as if it is not there. Those neutrinos would reach Earth first, about 3 hours before the light, because they escape the core immediately while the light has to fight its way out through thousands of kilometers of exploding star. Detectors buried deep underground in Japan, Italy, and the United States would see the neutrino burst. Alarms would go off. Phone calls would be made. Observatories all over the world would swing their telescopes toward Orion. Then the light would arrive. For the first few hours, Betelgeuse would brighten slowly, maybe doubling or tripling in brightness. Then it would start climbing fast. Within a day, it would outshine every star in the night sky except the Sun. Within a week, it would be as bright as the half moon. You would be able to see it in broad daylight. You would be able to read by its light at midnight. It would cast shadows. At its peak, Betelgeuse would glow at magnitude -12 or so, roughly equivalent to the brightness of the full moon but concentrated in a single point of light. That point would sit in Orion's shoulder for weeks, maybe months, slowly fading as the expanding debris cloud cooled and the radioactive elements powering the glow decayed into stable isotopes. Then, over the course of a few years, it would dim below naked eye visibility. Where Betelgeuse used to be, there would be a faint nebula, a cloud of glowing gas expanding outward at thousands of kilometers per second, seeding the surrounding space with oxygen, carbon, silicon, iron, and every other element the star had spent millions of years building. In a few 100,000 years, some of that gas would collapse into new stars, new planets, maybe new worlds where new forms of life would look up at their own night sky and wonder where they came from. That is what a supernova does. It ends one story and starts 1,000 others. And if it happened to Betelgeuse, we would have front row seats. The excitement was not just about the spectacle, although that was part of it. A supernova at 500 light-years would be close enough to study in extraordinary detail, close enough that our best instruments could resolve the expanding shockwave, watch the debris interact with the surrounding interstellar medium, measure the composition of the ejecta in real time. Close enough that gravitational wave detectors might, if the core collapsed asymmetrically, pick up ripples in space-time from the collapsing core. Close enough that neutrino detectors would record thousands of individual neutrino impacts, giving physicists a direct look at the physics of core collapse, something they have wanted for decades. The last nearby supernova visible to the naked eye was in 1987, SN 1987A, in the Large Magellanic Cloud, a small satellite galaxy about 170,000 light-years away. That explosion rewrote entire chapters of stellar astrophysics. It confirmed that neutrinos carried away most of the energy. It revealed that the progenitor star was a blue supergiant, not a red one, which nobody expected. It produced a neutron star, maybe, though nobody has definitively detected it yet. The light echo from the explosion is still propagating outward, illuminating surrounding dust clouds like a slow-motion firework. Betelgeuse would be closer by a factor of 300. The data would be orders of magnitude better. Entire PhD dissertations would be written on individual features in the spectrum. Telescope time would be booked for decades. It would be a career-defining event for every astronomer alive, which made the dimming in late 2019 tantalizing in a way that had nothing to do with spectacle and everything to do with the fact that we might actually be watching the opening moves of something we had only ever seen from a distance, except we probably were not. Most of the actual experts on Betelgeuse, the ones who had spent years studying its pulsations and atmosphere, were skeptical from the start. They pointed out that Betelgeuse had dimmed before, not this much, but it had dimmed. They pointed out that the two pulsation cycles were both near minimum, which meant a deeper than usual fade was expected. They pointed out that nothing in the star's spectrum suggested core collapse. The surface temperature was still normal. The radial velocity measurements, which track how fast the star's surface is moving toward or away from us, showed nothing unusual. The star was not contracting. It was not collapsing. It was just dim. But the data was ambiguous enough that nobody could rule out the supernova scenario entirely. And ambiguity is fertile ground for speculation. One detail that fueled the excitement came from an unexpected direction. On January 14, 2020, the LIGO and Virgo gravitational wave detectors picked up a short burst of ripples in space-time. The signal was weak, barely above the noise threshold, and the source localization was poor. The best estimate placed it somewhere in a broad patch of sky that included, among many other things, the constellation Orion. Someone noticed. Within hours, the idea was circulating online that maybe, just maybe, the gravitational wave burst was Betelgeuse's core collapsing. Maybe the neutrinos and the light had not arrived yet because they were still fighting their way out through the star's outer layers. Maybe we had just detected the actual moment of core collapse and the visible explosion would arrive any day. It was a beautiful idea. It was also almost certainly wrong. Gravitational wave detectors are not sensitive enough to detect a core collapse supernova from 500 light-years away unless the collapse is extraordinarily asymmetric, and even then the signal would be much weaker than what LIGO detected that day. The burst was later attributed to a glitch in the detector or possibly a very distant black hole merger, not a nearby supernova. But for a few days the possibility hung in the air, and observatories around the world pointed every available telescope at Betelgeuse just in case. Nothing happened. Betelgeuse stayed dim. It did not explode. It did not brighten suddenly. It just sat there, faint and red and utterly uncooperative with the narrative everyone was building around it. By February 2020, the dimming had stopped. The star had bottomed out at magnitude 1.6 or so, holding steady for a few weeks while astronomers scrambled to collect as much data as possible. Spectrographs recorded the star's light in exquisite detail, breaking it into thousands of wavelengths to search for any chemical signature that might hint at what was happening below the surface. Infrared telescopes watched for changes in temperature. Interferometers, instruments that combine light from multiple telescopes to achieve extremely high resolution, mapped the surface of the star itself, looking for spots or asymmetries that might explain the brightness drop. What they found was unexpected. The dimming was not uniform. The southern half of Betelgeuse had darkened dramatically, as if something had blocked the light from that side of the star. The northern half looked normal. It was as if someone had draped a curtain over one side of the star and walked away. That was not the behavior of a star preparing to explode. That was the behavior of a star doing something else entirely. Something nobody had seen before. By March 2020, Betelgeuse started to brighten again. Slowly at first, then faster. By April, it was back to near normal brightness, magnitude 0.5 or so, just slightly dimmer than before the whole event started. The speculation died down, the headlines moved on, the supernova watch was over. Except it was not over, because now astronomers had a new mystery. What had just happened? Why had Betelgeuse dimmed so dramatically, and why had only one side of the star darkened? The supernova hypothesis was off the table. Core collapse does not work that way. Whatever caused the Great Dimming, as it came to be called, it was not the opening act of an explosion. It was something else, something that had been hiding in plain sight for years, written into the star's own restless surface, telegraphed by cycles and pulses and long, slow rhythms that nobody had quite understood. The answer, when it finally came, would not just explain what happened in 2019, it would rewrite what we thought we knew about how giant stars die, how long they have left, and what happens in the final unstable years before they finally let go. The dust cloud was not supposed to be there. By March 2020, when astronomers had finally collected enough data to stop guessing and start measuring, the picture that emerged was stranger than the supernova hypothesis, and in some ways more unsettling. Betelgeuse had not begun collapsing. It had sneezed violently, and the sneeze had been so catastrophic that it had temporarily ripped away a chunk of the star's own skin and flung it into space, where it cooled, condensed, and hung in front of the southern hemisphere like a veil. The technical term is a surface mass ejection. The less technical term, coined by Andrea Dupree at the Harvard-Smithsonian Center for Astrophysics, is that Betelgeuse blew its top. This was not a metaphor. Between late 2019 and early 2020, Betelgeuse ejected a portion of its visible surface layer, the photosphere, sending a bubble of superheated plasma outward at roughly 200,000 miles per hour. That is about 320,000 kilometers per hour if you prefer metric. Fast enough to cross the distance from the Earth to the Moon in about 70 minutes. The amount of material involved was staggering. Estimates put the total mass ejected at several times the mass of Earth's moon. For comparison, the largest coronal mass ejections from our Sun, the kind that can knock out power grids and disrupt satellites when they hit Earth, carry maybe a few billion tons of material. The Betelgeuse event carried 400 billion times that much. 400 billion. Not 400, not 400,000. 400 billion times the mass of a large solar storm, all of it ripped from the surface of a star in a single sustained outburst that lasted roughly 3 months. Nobody had seen anything like it, not because it had never happened before, but because nobody had been watching closely enough when it did. Betelgeuse is not the kind of star you monitor every single night, unless you have a specific reason. It is big, it is bright, it is well studied, and until 2019 it had never done anything that required hourly attention. Professional astronomers checked in on it periodically, amateurs logged brightness estimates when they felt like it, and the general consensus was that Betelgeuse was doing what red supergiants do, pulsing, shedding mass slowly, inching toward an eventual explosion on a timescale measured in millennia. The Great Dimming changed that. Suddenly every telescope that could point at Orion was pointing at Orion. Hubble observed it. The Very Large Telescope in Chile observed it. ALMA, the Atacama Large Millimeter Array, watched it in radio wavelengths. Infrared observatories tracked its heat signature. Amateur astronomers with backyard setups contributed thousands of individual brightness measurements. For a few months, Betelgeuse was the most scrutinized object in the night sky after the Sun and the Moon. What all that scrutiny revealed was that the dimming had been caused by two overlapping phenomena, neither of which involved core collapse. The first was the ejection event itself. Something inside Betelgeuse, likely a particularly violent convective upwelling deep in the star's outer layers, had punched a bubble of gas up through the photosphere and launched it into space. Think of it like a lava lamp. The wax heats up at the bottom, becomes buoyant, rises to the top, cools, and sinks back down. Betelgeuse's outer envelope is doing the same thing constantly, but on a scale so grotesque that the rising blobs of hot plasma are each larger than entire stars. When one of these blobs reaches the surface, it does not sink back down gently, it breaks through, and if it is energetic enough, it keeps going. In 2019, one of those blobs kept going. It tore through the photosphere, likely in the southern hemisphere based on where the dimming was most pronounced, and carried a huge mass of gas with it. The gas was unimaginably hot when it left the surface, tens of thousands of degrees, glowing blue-white in the visible spectrum, and screaming outward on a ballistic trajectory that would carry it far beyond the star's normal radius. Then it hit cooler material. Betelgeuse is surrounded by a thin, extended atmosphere, a region where the density drops off gradually rather than stopping abruptly. The ejected plasma slammed into that cooler outer layer and began to lose energy. As it cooled, the chemistry changed. At temperatures above a few thousand degrees, matter exists as a plasma, individual atoms stripped of their electrons, too energetic to bond into molecules. Below that threshold, atoms start to stick together, molecules form, and if the conditions are right, those molecules can clump into solid grains, dust. This is where the dimming came from. The ejected gas cooled, condensed into microscopic particles of dust, mostly silicates and carbon compounds, and formed a cloud. That cloud, drifting outward and expanding as it went, passed directly between Betelgeuse and Earth. For several months we were looking at the star through a curtain of its own exhaled atmosphere, and the curtain blocked a significant fraction of the light. Hubble's observations, led by Dupree's team, caught the cloud in the act. Images taken in ultraviolet and visible wavelengths showed a distinct dark patch on the southern hemisphere of the star. Not a dimming of the entire surface, but a localized shadow, as if someone had painted over part of the star with a brush dipped in soot. Follow-up images over the next few months tracked the cloud as it expanded and gradually dispersed. By mid-2020, it had thinned out enough that Betelgeuse's light could punch through, and the star returned to something close to its normal brightness. The cloud itself, now too diffuse to block much light, continued drifting outward into interstellar space where it will eventually mix with the surrounding gas and become part of the raw material for the next generation of stars. The discovery that a dust cloud was responsible for the dimming solved one mystery and immediately created another. Dust clouds around red supergiants are not unusual. These stars are constantly shedding mass. Betelgeuse loses roughly 1 Earth mass of material every 10,000 years, puffed off gently by radiation pressure and stellar winds. That slow, steady leak is how red supergiants enrich the interstellar medium with heavy elements before they explode. The dust forms gradually in the cooler outer regions of the wind, condensing out of the gas like dew forming on grass. What made the 2019 event different was the violence. This was not a gentle leak. This was a rupture. And ruptures like that require a trigger. Something had to have destabilized the star's outer layers enough to punch a hole in the photosphere, and eject 400 billion coronal mass ejections worth of material in one go. The question was what? The answer, pieced together from months of data analysis, came down to shock waves. Betelgeuse is not a stable object. It is a dying star held together by forces that are barely in equilibrium. The core is fusing lighter elements into heavier ones, releasing energy that pushes outward and holds up the enormous weight of the overlying layers. The outer envelope, meanwhile, is so large and so diffuse that it has essentially decoupled from the core. The surface is too far away to feel the core's gravitational pull in any meaningful way. The result is an atmosphere that behaves less like the outer layer of a star and more like an independent weather system, churning and convecting and pulsing on its own timescales. That convection is violent. Deep inside the envelope, hot plasma rises toward the surface in columns hundreds of millions of kilometers wide. When it reaches the photosphere, it releases its heat, cools, and sinks back down, only to be reheated and rise again. The process generates shock waves, pressure fronts that ripple outward through the atmosphere like sound waves through air, compressing and heating the gas as they pass. Most of these shock waves are relatively weak. They contribute to the star's pulsations, the regular expansion and contraction that makes Betelgeuse a variable star, but they do not fundamentally disrupt the structure. Every so often, though, conditions align and a particularly strong shockwave forms. Maybe two convective cells merge. Maybe a pulse in the core's fusion rate sends a surge of energy outward. Maybe it is just bad luck, the stellar equivalent of a rogue wave on the ocean. Whatever the cause, the shockwave that hit Betelgeuse's photosphere in late 2019 was strong enough to do serious damage. Data from the Hubble Space Telescope and ground-based observatories showed that in the months leading up to the dimming, the star's southern hemisphere had developed an unusually large cool spot. Not a sunspot, which is a magnetic phenomenon, but a region where the surface temperature had dropped by roughly 250 degrees Fahrenheit compared to the surrounding area. That is about 140 degrees Celsius. For a star whose surface sits at around 6,000 degrees Fahrenheit, a drop of 250 degrees is barely noticeable in terms of total energy output, but it is enough to change the local conditions dramatically. Cooler gas is denser. Denser gas is less buoyant. When the shockwave hit that region, it did not just compress the gas and move on, it punched through. The cool spot, already sitting at a lower temperature and higher density than the surrounding photosphere, acted like a weak point. The shockwave drove a wedge into it, lifted a massive bubble of material and launched it into space. That bubble carried the cool spot with it, or rather, it carried the gas that had been forming the cool spot. As the ejected material climbed out of the star's gravitational well, it cooled further, eventually dropping below the condensation temperature for silicate dust. The dust formed, scattered the starlight, and from Earth's perspective, Betelgeuse dimmed. The whole process, from shockwave to ejection to dust cloud to dimming, took about a year. Observations from early 2019, before anyone realized something unusual was happening, show shockwaves propagating through the photosphere as early as January. By mid-year, the southern hemisphere had developed the cool spot. By October, the ejection had begun. By December, the dust cloud was thick enough to block a substantial fraction of the star's light. By February 2020, the dimming had peaked. By April, the cloud had dispersed enough for the star to brighten again. One of the more surreal details to come out of the post-dimming analysis was just how little of Betelgeuse's surface had been affected. The dust cloud, despite being massive by any human standard, covered only about 1/4 of the star's visible disk. The northern hemisphere, the eastern limb, and most of the western side were completely unaffected. The light from those regions reached Earth just fine. It was only the southern quarter that had been obscured. This asymmetry is what tipped astronomers off that the dimming was not a global phenomenon. If the entire star had dimmed uniformly, the explanation would almost certainly have involved something happening in the core, a change in the fusion rate, a shift in the internal structure, something that affected the star's overall luminosity. But the lopsided dimming pointed to something local, something happening in the outer layers, something that had nothing to do with whether the star was about to explode. Interferometric observations from the European Southern Observatory's Very Large Telescope, using an instrument called MATIS, captured direct images of the star's surface in unprecedented detail. MATIS works by combining light from 4 separate 8.2-meter telescopes, effectively creating a single instrument with a resolution equivalent to a telescope more than 100 meters across. That is not enough to see surface features on most stars, which are too small and too far away to resolve. But Betelgeuse is close enough and large enough that MATIS can actually map its surface, picking out bright spots, dark spots, and temperature variations across the disk. The MATIS images from late 2019 and early 2020 showed exactly what the models predicted: a large dark region on the southern hemisphere, cooler than the surrounding surface by a few hundred degrees, with clear evidence of outflowing material. Follow-up observations in 2021, after the dust cloud had dispersed, showed the region returning to normal. The cool spot was gone. The surface looked uniform again. Betelgeuse had recovered. But the event left a scar in the data. By comparing observations taken before, during, and after the dimming, astronomers were able to reconstruct a timeline of what had happened and, more importantly, figure out how often events like this occur. The answer was unsettling, probably more often than we think. Betelgeuse's surface gravity is absurdly weak, about 10,000 times weaker than the Sun's. If you were standing on the surface of Betelgeuse, assuming you could find something solid to stand on, which you could not because the star does not have a surface in the traditional sense, you would weigh 10,000 times less than you do on Earth. A 100-kilogram person would weigh 10 grams, the weight of 2 nickels. That is not enough gravity to hold an atmosphere together against even modest outward pressure. Any significant upwelling of hot gas from below, any strong shockwave, any convective burp, can and will eject material into space. This means Betelgeuse is constantly shedding bits of itself, not in a smooth, continuous wind like the Sun, but in episodic bursts. Small ones happen all the time, too small and too brief to notice from Earth. Larger ones, like the 2019 event, happen less often but are dramatic enough to leave observable signatures. The largest ones, which may happen once every few thousand years or so, could eject even more mass, possibly enough to affect the star's internal structure and evolution. The 2019 event, in other words, was not a sign that Betelgeuse is about to explode. It was a sign that Betelgeuse is doing what massive dying stars do, losing mass, unstably, violently, in ways that we are only just beginning to understand because we have only just begun watching closely enough to catch them in the act. One of the key findings from the post-dimming studies was that Betelgeuse's intrinsic luminosity, the total amount of energy it radiates into space, did not change during the event. Infrared observations, which see through dust much more effectively than visible light, showed the star glowing just as brightly as it had before the dimming. The energy was still there. It was just being blocked from our line of sight by the dust cloud. This ruled out any explanation that required the star to actually dim, any scenario where the core's energy output dropped or the fusion rate changed. The dimming was entirely due to extinction, the technical term for light being absorbed or scattered by intervening material. That detail, more than anything else, killed the supernova hypothesis. A star preparing to collapse does not block its own light with dust. It dims because the core is running out of fuel, because the outer layers are contracting, because the energy generation is dropping. Betelgeuse's core was still humming along, fusing elements, pumping out energy at the same rate it had been for thousands of years. The only thing that had changed was the amount of junk floating between us and the star. The realization that the Great Dimming was essentially a giant dust cloud led to an interesting follow-up question. If Betelgeuse can eject this much material in one event, and if events like this happen every few thousand years or so, how much mass has it lost over the last 100,000 years? And how much mass will it have left by the time it finally does explode? Current models of stellar evolution predict that red supergiants lose a significant fraction of their mass during the final stages of their lives. The Sun, for comparison, will lose about half its mass during its red giant phase, puffing off its outer layers in a planetary nebula that will eventually disperse into space. Betelgeuse, being much more massive and much more unstable, will lose even more. Estimates suggest it started its life with about 20 solar masses and has already shed at least a third of that, maybe more. The 2019 ejection event, despite being the largest observed in modern times, only accounted for a tiny fraction of the star's total mass. A few Earth masses out of a total of 10 to 15 solar masses is negligible, a rounding error. But if events like this happen regularly, and if Betelgeuse is also shedding mass continuously through a slower stellar wind, the cumulative loss over tens of thousands of years adds up. By the time the core finally runs out of fuel and collapses, Betelgeuse may have lost so much mass that its final explosion is weaker than it would have been if the star had stayed intact. This matters because the properties of a supernova, how bright it gets, how fast it expands, how much heavy elements it produces, depend critically on the mass of the exploding star. A 15 solar mass star produces a different kind of supernova than a 10 solar mass star. If Betelgeuse has been shedding mass faster than models predict, and if that mass loss is driven in part by these episodic ejection events, then our predictions for what will happen when it finally goes are almost certainly wrong. That brings us to one of the more uncomfortable truths to emerge from the Great Dimming. We do not understand mass loss in red supergiants nearly as well as we thought we did. For decades, the standard model assumed that mass loss was smooth, driven by radiation pressure and stellar winds, something you could calculate with a reasonably simple set of equations. The 2019 event showed that assumption was incomplete. Betelgeuse is not losing mass smoothly, it is losing it in chunks, violently, unpredictably. And if Betelgeuse is doing this, other red supergiants are probably doing it too. We just have not been watching them closely enough to notice. There is a broader point here. The Great Dimming was not just a strange event involving a single star. It was a preview of the kind of instabilities that dominate the final years of massive stellar evolution. Stars like Betelgeuse do not die quietly. They thrash, they convulse, they blow off pieces of themselves in fits and starts, sculpting the space around them into a chaotic mess of gas, dust, and shockwaves. When the core finally collapses, it does so inside an envelope that has already been partially disassembled, an envelope that is no longer the smooth spherical shell the textbooks describe. That messy pre-supernova environment affects everything. It affects how bright the explosion looks from Earth. It affects how the debris interacts with surrounding material. It affects what kind of remnant gets left behind, whether it is a neutron star or a black hole, and what that remnant looks like. If we want to understand supernovae, We need to understand mass loss. And if we want to understand mass loss, we need to watch more stars like Betelgeuse go through more events like the Great Dimming. The dust cloud that caused all the excitement in 2019 and 2020 is still out there, by the way. It has dispersed and thinned and is no longer dense enough to block any meaningful amount of light, but it has not vanished. It is drifting outward through space at a few hundred kilometers per second, mixing with the wind material that Betelgeuse has been shedding for millennia. In a few thousand years, it will have traveled far enough that it will be indistinguishable from the general interstellar medium. The atoms that made up that cloud, the silicon and oxygen and carbon that condensed into dust grains when the ejected gas cooled, will eventually be recycled into new stars, new planets, new worlds, but not yet. Right now, the cloud is still close enough to Betelgeuse that sensitive infrared telescopes can see it as a faint warm shell surrounding the star. And embedded in that shell, invisible to our instruments but there nonetheless, is the record of what happened in 2019. A snapshot of a massive star in the act of tearing itself apart, one convulsive shudder at a time. The real mystery, the one that kept astronomers digging through the data long after the dimming had ended and the headlines had moved on, was not what caused the ejection. Shock waves and convection and weak surface gravity explained that well enough. The real mystery was timing. Why did it happen in 2019? Why not 2015 or 2025? Why, after decades of relatively stable behavior, did Betelgeuse suddenly decide to blow its top? The answer to that question would not come from studying the star's atmosphere or its dust clouds. It would come from looking deeper, much deeper, at something hiding in the data that nobody had thought to check, something that had been there all along, orbiting silently in the dark, tugging on Betelgeuse's bloated envelope with a gravitational pull just strong enough to tip the balance. The shockwave explanation was elegant. It fit the data cleanly. It explained the cool spot, the ejection, the dust cloud, the asymmetry, all of it. For a few months after the Great Dimming ended and Betelgeuse returned to normal brightness, the scientific community largely considered the case closed. Betelgeuse had burped, violently, spectacularly, but just a burp. The star was not exploding. It was not collapsing. It was doing what red supergiants do, losing mass in episodic fits driven by internal convection and surface instability. Move along. Nothing to see here, except a few researchers were not satisfied. Not because the shockwave model was wrong, but because it was incomplete. It explained how the ejection happened. It did not explain why it happened when it did. Betelgeuse had been observed for more than a century. Astronomers had catalogued its pulsations, mapped its brightness variations, tracked its irregular flickering. In all that time, it had never dimmed this dramatically. The Great Dimming was not just unusual, it was unprecedented, and unprecedented events tend to have triggers. Something had to have destabilized the star's atmosphere in late 2019, enough to generate a shockwave powerful enough to punch a hole in the photosphere and eject several moon masses of material into space. The convection-driven shockwave model explained the mechanism. It did not explain the timing. Andrea Dupree at the Harvard-Smithsonian Center for Astrophysics had been studying Betelgeuse for decades. She had led the Hubble observations during the dimming. She had been one of the first to propose that the event was driven by a surface mass ejection rather than core collapse. And after the dust settled, literally she kept looking at the data, not just the dimming data but the older data. Years of spectroscopic observations, Doppler measurements, radial velocity curves, anything that tracked how Betelgeuse's atmosphere moved over time. What she found was a pattern, a faint one, buried under the noise of the star's normal pulsations, but there, every 2,000 days or so, give or take a few months, something in Betelgeuse's spectrum changed. The velocities of the gas in the outer atmosphere shifted, not uniformly, but in a localized region, as if something had passed through and stirred the gas like a spoon through soup. The signal was weak. Most of the time, it was drowned out by the star's chaotic convective motions. But if you knew what to look for, and if you had enough data spanning enough years, you could see it. Dupree and her team went back through archival observations from Hubble, from ground-based telescopes in the Canary Islands and Arizona, from spectrographs that had been pointing at Betelgeuse on and off for the better part of 20 years. They pulled every measurement they could find that showed how fast the gas in Betelgeuse's atmosphere was moving toward or away from Earth. Those measurements are encoded in the star's spectral lines. When gas moves toward you, the wavelength of the light it emits gets compressed, shifted toward the blue end of the spectrum. When it moves away, the wavelength stretches, shifted toward the red. By measuring how much a given spectral line has shifted, you can calculate the velocity of the gas producing that line. For most stars, this technique gives you a single number. The star as a whole is moving toward or away from you at some velocity, and that is it. For Betelgeuse, the situation is more complicated. Betelgeuse is so large and so close that high-resolution spectrographs can pick out individual regions of the star's atmosphere. Different parts of the surface are moving at different speeds because the star is rotating, because convection is churning the gas, because shock waves are propagating outward, because the whole atmosphere is a seething, chaotic mess. When you point a spectrograph at Betelgeuse, you do not get a single spectral line. You get a blurred, smeared-out line, the sum of contributions from every part of the star's visible disk, each moving at a slightly different velocity. Most of the time, that smearing is symmetrical. The parts of the star moving toward you are balanced by the parts moving away, and the line looks roughly centered with broad wings on either side. But if something disturbs the atmosphere in a particular region, say a large plume of gas rising faster than the surrounding material, or a dense clump sinking back down, the symmetry breaks. The spectral line develops an asymmetry, a bump or a dip that shows up as a deviation from the smooth average. Dupree's team found those bumps, and they found that the bumps repeated on a cycle of roughly 2,100 days. Every 6 years or so, a disturbance appeared in Betelgeuse's spectrum, moved across the star's disk, and faded. The disturbance was always localized. It did not affect the entire atmosphere. It showed up in one region, stirred the gas, left a wake, and moved on. That behavior pointed to something moving through the atmosphere, not a shockwave propagating outward from the core, which would affect the entire star more or less uniformly. Something localized, something with mass, something exerting a gravitational pull strong enough to sweep up gas as it passed. The simplest explanation was a companion star, another star, smaller and fainter than Betelgeuse, orbiting so close that it was embedded inside Betelgeuse's extended atmosphere. The companion's gravity, as it moved through the tenuous outer layers of the supergiant, would act like a gravitational plow, compressing the gas in front of it and leaving a trail of denser material behind. That trail would show up in the spectrum as a region of enhanced velocity, a wake, exactly the kind of disturbance Dupree's team had been seeing. Binary star systems are not unusual. In fact, they are more common than single stars. Surveys suggest that more than half of all stars in the galaxy are part of binary or multiple star systems, two stars orbiting a common center of mass, bound together by gravity, evolving side by side over billions of years. Sometimes the stars are well separated, orbiting each other at distances of hundreds or thousands of astronomical units. so far apart that they barely interact. Other times, they are close, orbiting within a few stellar radii of each other, exchanging mass, distorting each other's shapes, locked in a slow gravitational dance that can last for millions of years or end catastrophically in a merger or a supernova. The idea that Betelgeuse might be part of a binary system was not new. Astronomers had suspected it for decades. Betelgeuse has what is called a long secondary period, a slow variation in brightness that runs on a timescale of about 2,000 days, much longer than the star's main pulsation cycle. Long secondary periods are common in red supergiants, and the leading explanation for them is binarity. A companion star, orbiting at the right distance, could gravitationally perturb the supergiant's atmosphere, triggering enhanced mass loss or amplifying convective instabilities in a way that produces a regular brightness variation. But suspecting a companion and actually finding one are two very different things. Betelgeuse is so bright and so large that any companion small enough to hide inside its atmosphere would be completely overwhelmed by the supergiant's light. You could not see it directly, not with any telescope currently in operation. The companion, if it existed, would have to be inferred indirectly through its gravitational effects on the surrounding gas. That is exactly what Dupree's team did. By mapping the velocity structure of Betelgeuse's atmosphere over multiple cycles, they were able to track the companion's orbit. The wake appeared in the spectrum every 2,100 days, moving across the star's disk at a steady rate, following a path consistent with a roughly circular orbit. The orbital period matched the long secondary period that had been noted in historical brightness data going back more than a century. The companion was not a new discovery. It had been there all along, hiding in plain sight, announced by its gravitational fingerprints but never directly seen. In 2025, before the companion had been definitively confirmed through all the necessary cross-checks and modeling, the team gave it a name, Siwarha, taken from a Tonga word that translates roughly to companion or sibling. Naming an object before you have conclusively proven it exists is unusual in astronomy, where the standard practice is to catalogue things with dry alphanumeric designations until their properties are nailed down. But Dupree and her colleagues were confident enough in the data, and the discovery was significant enough that they went ahead and gave it a name. Siwarha orbits Betelgeuse at a distance of about 4 astronomical units. For scale, 1 astronomical unit is the distance from the Earth to the Sun, about 93 million miles or 150 million kilometers. 4 astronomical units is roughly the distance from the Sun to the asteroid belt, a bit closer than Jupiter's orbit. In the context of the solar system, that would be a respectable distance, far enough that you would need a decent telescope to see details. In the context of Betelgeuse, it is nothing. Betelgeuse's radius, depending on how you define the edge of its atmosphere, is somewhere between 500 and 1,000 times the radius of the Sun. That translates to something like 3 to 6 astronomical units. Siwarha is not orbiting outside Betelgeuse, it is orbiting inside. Let that sink in for a second. There is a star, a complete star with its own nuclear fusion and its own gravitational field and its own atmosphere, orbiting through the outer layers of another star. It is not skimming the surface. It is not grazing the edge. It is deep inside, plowing through gas that is still technically part of Betelgeuse's extended envelope, carving out a wake as it goes. The mass of Siwarha is estimated at about 1.5 times the mass of the Sun. That is not a small star. It is not a red dwarf or a brown dwarf or some faint stellar remnant. It is a decent-sized main sequence star, probably a spectral type A or late B, hot and blue and luminous in its own right. Under normal circumstances, a star like that would be easily visible through a telescope, but Siwarha is not under normal circumstances. It is embedded in a fog of glowing hydrogen so thick and so bright that its own light is completely swamped. Imagine trying to spot a flashlight inside a searchlight beam. That is the observational challenge here. The only reason we know Siwarha is there is because of the wake. As the companion moves through Betelgeuse's atmosphere, its gravity compresses the surrounding gas. That compression heats the gas slightly and increases its density. The denser gas emits more light at certain wavelengths, specifically in the spectral lines of ionized metals and hydrogen. Those lines show up as bright spots or enhanced emission regions in high-resolution spectra, and because the compressed gas is moving, dragged along by the companion's orbital motion, the spectral lines are Doppler shifted. By measuring the shifts, you can calculate the velocity of the gas. By tracking how the velocity changes over time, you can reconstruct the companion's orbit. The technique is called kinematic mapping, and it is one of the few ways to detect a star that is too faint or too obscured to see directly. It has been used to find black holes in binary systems, to map the orbits of stars around the supermassive black hole at the center of the Milky Way, and now to find a companion star hiding inside a red supergiant's atmosphere. One of the more striking results from the analysis was how well the orbital period of Siwarha matched up with the timing of major mass loss events in Betelgeuse's recent history. The Great Dimming in 2019 happened roughly 6 years after the previous suspected dimming event in late 2013, which had been noted but not studied in detail at the time. 6 years is the orbital period of Siwarha. Every time the companion completes one orbit, it passes through a particular region of Betelgeuse's atmosphere, and shortly afterward, the star ejects a large mass of material. The connection is not coincidental. Siwarha's gravity, as it moves through the dense lower layers of the atmosphere, does more than just compress gas and leave a wake. It also triggers instabilities. Betelgeuse's outer envelope is only barely bound by gravity. The surface gravity is so weak that even a modest external perturbation can push material over the edge, literally ejecting it into space. Siwarha, passing through every 6 years, provides that perturbation. Its gravitational pull drags gas upward, amplifies convective motions, destabilizes regions that were already close to the breaking point. The result is a mass ejection event, timed to the companion's orbit. This is not a new idea. Binary interactions have been known to trigger mass loss in evolved stars for decades. Classical novae, for example, are caused by a white dwarf in a binary system, pulling material off a companion star until enough hydrogen piles up on the white dwarf's surface to ignite in a runaway fusion reaction. Symbiotic stars, systems where a red giant is paired with a hot compact companion, exhibit periodic outbursts driven by the gravitational and radiative influence of the companion. What makes the Betelgeuse-Siwarha system unusual is the scale. Red supergiants are the largest stars in the universe. Their atmospheres extend for hundreds of millions of kilometers. Finding a companion embedded that deep and demonstrating that its orbit directly shapes the supergiant's mass loss behavior is unprecedented. One of the key pieces of evidence that convinced the broader astronomical community that Siwarha was real came from hydrodynamic simulations. Dupree's team, working with computational astrophysicists, built detailed three-dimensional models of Betelgeuse's atmosphere and then added a companion star moving through it on a 6-year orbit. The simulations tracked how the gas responded to the companion's gravity, how the wake formed, how the density and velocity structure evolved over time. Then they synthesized what the star's spectrum would look like as seen from Earth, taking into account the geometry of the orbit, the line of sight effects, and the blending of light from different parts of the atmosphere. The synthetic spectra matched the observations. The bumps and asymmetries in the real data showed up in the simulated data at the same times, in the same spectral lines, with the same velocities. That agreement between models and observations is one of the strongest forms of confirmation in astrophysics. It means the story you are telling is not just plausible, it is quantitatively consistent with the physics. The simulations also revealed something unexpected. The wake left by Siwarha is not a simple trail of compressed gas. It is more like a spiral. As the companion orbits through the atmosphere, the gas it disturbs does not just fall back into place. It continues to move, carried along by the star's rotation and its own turbulence, spreading out into a long curved streamer that wraps partway around Betelgeuse's equator. That streamer, over the course of several months, gradually disperses and mixes back into the ambient atmosphere. But while it exists, it creates a region of enhanced density and enhanced instability, a weak point in the star's outer layers where the next shockwave is more likely to punch through. This explains why the Great Dimming happened when it did. The shockwave that triggered the ejection was not an isolated event. It was the culmination of two processes acting together. First, Betelgeuse's internal convection generated a strong upwelling in the southern hemisphere, creating the cool spot and setting the stage for an ejection. Second, Siwarha, on its regular 6-year orbit, passed through that region at almost exactly the same time, amplifying the instability and providing the extra gravitational kick needed to launch the material into space. Timing, in this case, was everything. If Siwarha had been on the other side of its orbit, the shockwave might have still disrupted the cool spot, but the ejection would have been weaker, the dust cloud thinner, and the dimming less dramatic. The fact that the companion happened to be in the right place at the right time turned what might have been a minor mass loss event into the most spectacular dimming episode in Betelgeuse's recorded history. The discovery of Siwarha changes the entire narrative around Betelgeuse. For decades, astronomers treated it as a single star, a solitary red supergiant evolving in isolation, driven purely by internal processes. The pulsations, the mass loss, the convection, all of it was assumed to be intrinsic, the natural behavior of a massive star nearing the end of its life. The discovery that Betelgeuse has been part of a binary system all along means that much of what we thought we understood was incomplete. The pulsations are not purely intrinsic, they are modulated by the companion's orbit. The mass loss is not purely driven by radiation pressure and stellar winds. It is amplified by gravitational interactions. The long secondary period, the irregular brightness variations, the episodic ejections, all of it is shaped, at least in part, by the presence of Siwarha. Binary interactions do not just complicate stellar evolution, they fundamentally change it. A star in a binary system does not evolve the same way a single star does. The companion's gravity can strip away the outer layers, alter the rotation rate, trigger instabilities that would not occur otherwise. In extreme cases, the companion can even prevent a supernova from happening at all, siphoning off so much mass that the core never gets heavy enough to collapse. More commonly, the companion changes the timing and the properties of the explosion, affecting how bright it gets, how fast the debris expands, what kind of remnant gets left behind. For Betelgeuse, the key question now is how much Siwarha has affected the star's evolution so far, and how much it will affect the final explosion. The answer to that question is not clear yet. The models are still being refined. But the fact that we even have to ask it is a sign of how much the discovery has shifted the conversation. Betelgeuse is no longer just a dying star. It is a dying star with a companion, and the companion is not a passive bystander. It is an active participant in the death. One of the more uncomfortable implications of the discovery is that if Betelgeuse is part of a binary system, and if that binary interaction has been shaping its mass loss and evolution for thousands or even millions of years, then every prediction we have made about when it will explode is potentially wrong. The standard models of red supergiant evolution assume a single star. They do not account for a companion stripping away mass, triggering ejections, altering the internal structure. If Betelgeuse has lost more mass than the models predict because of interactions with Siwarha, then its core is smaller, its envelope is thinner, and its remaining lifetime is different. Maybe longer, maybe shorter, but definitely different. That uncertainty is frustrating. It is also exciting, because it means we are no longer guessing about Betelgeuse based on general principles and average stars. We are studying Betelgeuse as it actually is, a messy, complicated binary system with a history of instability and a future that depends on factors we are only just beginning to untangle. The discovery of Siwarha did not answer the question of when Betelgeuse will explode. It made the question harder. But it also gave us the tools to finally answer it properly by understanding the star not as an isolated object, but as half of a pair locked in a gravitational embrace that has been shaping its fate for longer than humans have been watching. The discovery of Siwarha did not just add a detail to Betelgeuse's biography. It ripped up the entire biography and forced astronomers to start over. For decades, the standard model of Betelgeuse's evolution went something like this. The star was born 15 or 20 million years ago in a molecular cloud somewhere in Orion. It began life with about 15 to 20 times the mass of the Sun, maybe a bit more. It spent the first few million years fusing hydrogen into helium in its core, burning through fuel at a rate thousands of times faster than the Sun, because massive stars live hard and die young. When the hydrogen ran out in the core contracted, heated up, and started fusing helium into carbon and oxygen. The outer layers, no longer supported by the hydrogen fusion that had been holding them up, expanded outward. The star became a red supergiant. From there, the timeline stretched out over the next 100,000 years or so. The core would continue working its way through progressively heavier elements, fusing carbon into neon, neon into oxygen, oxygen into silicon, silicon into iron. Each stage would run faster than the last because each reaction released less energy and required higher temperatures. Eventually, maybe 100,000 years from now, the core would fill with iron, fusion would stop, the core would collapse. The outer layers would fall inward, hit the incompressible neutron-degenerate core, and rebound outward in a supernova explosion that would briefly outshine the entire galaxy. Clean, predictable, textbook stellar evolution. The kind of story you could teach to undergraduates without needing to add a bunch of caveats and footnotes. Except Betelgeuse is not a single star, it is part of a binary system. And binary stars do not evolve the way single stars do. They interact, they exchange mass, they distort each other's shapes, strip away each other's atmospheres, alter each other's internal structures. In some cases, the interactions are mild, barely noticeable over the star's lifetime. In other cases, they are catastrophic, ending in mergers, nova or supernova that would never have happened if the stars had been alone. The moment you add a companion to Betelgeuse's story, every single assumption in the standard model becomes negotiable. The mass of the star at birth, no longer straightforward, because you now have to account for how much mass it may have lost or gained through interactions with the companion. The age of the star, harder to pin down, because binary interactions can speed up or slow down the rate at which a star burns through its fuel. The timeline to supernova? Completely up for grabs, because the presence of the companion changes how fast the core evolves and how much of the envelope gets stripped away before the final collapse. Stellar evolution is already complicated when you are dealing with a single star. Add a second star into the mix, and the problem becomes exponentially harder. You are no longer just modeling one object. You are modeling two objects plus the gravitational field between them, plus the flow of gas from one star to the other, plus the tidal distortions, plus the orbital decay, plus the angular momentum transfer, plus a dozen other effects that all feed back on each other in nonlinear ways. The equations do not have clean analytical solutions. You have to run simulations, numerical models that step forward in time and calculate what happens at each stage based on the current state of the system. And those simulations are only as good as the physics you put into them. If you miss a key process or underestimate the strength of an interaction, your predictions will be wrong. For Betelgeuse, the first question the models had to answer was whether Siwarha had always been part of the system or whether it had been captured later. Capture scenarios, where one star grabs another out of interstellar space, are rare. The velocities and geometries have to line up almost perfectly for a capture to succeed, and even then the resulting orbit is usually highly eccentric, a long stretched ellipse rather than a circle. Siwarha's orbit, based on the 6-year period and the velocity measurements from the spectral wake, appears to be roughly circular. That points strongly toward a common origin. Both stars likely formed together in the same molecular cloud, condensing out of the same collapsing gas clump, bound to each other from birth. If that is correct, and most astronomers working on the problem think it is, then Siwarha has been orbiting Betelgeuse for the entire 15 to 20 million year lifetime of the system. That means every stage of Betelgeuse's evolution, from its time on the main sequence to its current red supergiant phase, has been shaped by the companion's presence. The interactions were probably weak at first. When Betelgeuse was still a main sequence star, compact and dense, its radius was much smaller, maybe 10 or 15 times the radius of the Sun. Siwarha, orbiting at a distance of roughly 4 astronomical units in today's configuration, would have been well outside the primary star's atmosphere. The two stars would have been gravitationally bound, orbiting a common center of mass, but not interacting in any direct physical way. No mass transfer, no tidal distortions, just two stars sharing an orbit. That changed when Betelgeuse left the main sequence and began to swell. As the outer envelope expanded, the surface of the star moved outward, eventually reaching a radius of several hundred times the Sun's. At some point during that expansion, Betelgeuse's atmosphere engulfed Siwarha. The companion, which had been orbiting in empty space, suddenly found itself embedded in the outer layers of the supergiant, surrounded by a thin but still substantial atmosphere of hydrogen and helium. That is when the real interactions began. A star moving through the atmosphere of another star experiences drag. Not air drag in the familiar sense, but gravitational drag, a friction-like effect caused by the companion's gravity pulling on the surrounding gas. The gas near the companion gets compressed, heated and accelerated. As the companion moves forward, it leaves a wake of disturbed material behind it, a trail of higher density gas that gradually disperses back into the ambient atmosphere. That wake carries momentum. Over time, the momentum transfer slows the companion down, robbing it of orbital energy and causing it to spiral inward. This process is called dynamical friction, and it is one of the main ways that objects lose energy when they move through a diffuse medium. Satellites in low Earth orbit experience it when they skim through the upper atmosphere. Black holes at the centers of galaxies experience it when they move through clouds of stars. And Siwarha is experiencing it now, plowing through Betelgeuse's extended envelope, losing energy with every orbit. The timescale for this inward spiral depends on the density of the gas and the mass of the companion. A more massive companion experiences stronger drag and spirals in faster. A denser atmosphere produces more friction. For Siwarha, with a mass of about 1.5 solar masses moving through gas with a density of roughly 10 to the power of -8 grams per cubic centimeter, the orbital decay time is estimated to be somewhere between 10,000 and 100,000 years. That is the amount of time Siwarha has left before it spirals all the way into Betelgeuse's core and merges with the supergiant. 10,000 to 100,000 years, not millions, not billions. The companion is on a collision course, and the collision is going to happen soon, at least by astronomical standards. The fact that Siwarha is still orbiting inside the envelope, rather than having already merged, tells us something important about the timeline. If Betelgeuse had been a red supergiant for millions of years, Siwarha would already be gone. The companion would have spiraled in, been torn apart by tidal forces, and merged with the core long ago. The fact that it is still there, still intact, still carving out a wake every 6 years, means Betelgeuse became a red supergiant relatively recently, probably within the last million years or so, maybe less. That constraint feeds directly into models of the star's age and its remaining lifetime. If Betelgeuse only recently expanded to red supergiant size, and if it started its life with a mass closer to 15 solar masses rather than 20, then it is younger than many previous estimates suggested. Instead of being 15 or 20 million years old, it might be closer to 10 million. And if it is younger, then it has more fuel left. Its core is less evolved. The clock to supernova is not ticking as fast as we thought. This is where the revised models, the ones that account for Siwarha's presence, diverge most sharply from the old single-star predictions. The single-star models, based on a star evolving in isolation, assumed Betelgeuse had already burned through most of its nuclear fuel and was deep into the red supergiant phase, maybe nearing the end of helium burning or even starting to fuse carbon. Those models gave the star a remaining lifetime of about 100,000 years, maybe as little as 10,000 if you pushed the parameters toward the more evolved end of the range. The binary models tell a different story. When you account for mass loss driven by interactions with Siwarha, the picture changes. Betelgeuse has been shedding mass faster than a single star would because the companion's gravity amplifies instabilities in the outer envelope and triggers episodic ejection events like the Great Dimming. That faster mass loss strips away the outer layers more quickly, but it also reduces the weight pressing down on the core. A lighter envelope means the core does not have to burn as hot to support the overlying layers. Lower core temperatures mean slower fusion rates. Slower fusion means the star takes longer to work its way through the remaining fuel. The net effect is that Betelgeuse's lifetime gets extended, not by a little, by a lot. Instead of 100,000 years, the new models suggest Betelgeuse could have several 100,000 years left. Some estimates push it even higher, closer to 1,000,000 years, depending on how much mass the star loses over the next few orbital periods and how much of that mass comes from the outer envelope versus the deeper layers that affect the core's evolution. The uncertainty is large, larger than anyone in the field is comfortable with, but the direction of the revision is clear. Siwarha is buying Betelgeuse time. This is counterintuitive. When most people hear that a star has a companion stripping away its atmosphere, The natural assumption is that the interaction would shorten the star's life, hastening its demise. And in some binary systems, that is exactly what happens. If the companion is massive enough and close enough, it can strip away so much material that the primary star's core is exposed prematurely, forcing it to evolve faster. But Betelgeuse is different. The mass being stripped away is not coming from the core. It is coming from the bloated outer envelope, the vast diffuse shell of hydrogen and helium that makes up most of the star's volume, but only a small fraction of its mass. Losing that material does not affect the core's fusion rate directly. What it does is reduce the gravitational pressure on the core, allowing it to fuse more slowly. Think of it like this. Imagine you are at the bottom of a deep ocean, holding up a weight. The weight represents the core of the star, trying to collapse under its own gravity. The water around you represents the outer envelope, pressing down on you from all sides. The deeper you are, the higher the pressure, and the harder you have to push to hold the weight up. Now imagine someone starts draining water out of the ocean. The pressure drops. You do not have to push as hard. The weight is still the same, but the load you are supporting has decreased. That is what happens when Betelgeuse loses mass from its envelope. The core is still there, still fusing helium or carbon, but the pressure on it has decreased. It can afford to burn more slowly. The fuel lasts longer. Of course, there is a limit to how much this helps. If you strip away too much of the envelope, the core eventually runs out of insulation and starts losing energy directly to space. That can actually speed up the final stages of evolution, forcing the star to burn its remaining fuel faster to compensate for the energy loss. But Betelgeuse is nowhere near that limit. Even after the Great Dimming and all the other mass loss events over the last few 100,000 years, the envelope is still enormous, still optically thick, still doing its job of trapping energy and regulating the core's temperature. The companion is not stripping the star down to its core. It is trimming the edges, sculpting the envelope, keeping the star in a kind of extended red supergiant phase that would not last as long if Betelgeuse were evolving alone. One of the key insights from the binary models is that Siwarha's influence is not just about mass loss, it is also about angular momentum. A binary system contains a large amount of angular momentum stored in the orbital motion of the two stars. As the companion spirals inward, that angular momentum has to go somewhere. Some of it gets transferred to the gas in the envelope, spinning it up, increasing the rotation rate of the outer layers. Some of it gets radiated away as gravitational waves, ripples in spacetime that carry energy outward at the speed of light. The process is slow but relentless, and it changes the internal structure of the supergiant in subtle ways. Faster rotation in the envelope means more efficient mixing of material between the core and the surface. Elements that were forged in the core and would normally stay buried get dredged up to the surface where they can be observed in the star's spectrum. That mixing can also affect the fusion rate by transporting fresh fuel into the burning regions and carrying away the ash, the helium, and heavier elements that would otherwise clog up the core and slow down the reactions. For Betelgeuse, the rotational effects are probably small compared to the direct gravitational perturbations from Siwarha, but they are not negligible. Every time the companion completes an orbit, it gives the envelope a tiny spin-up. Over millions of years, those tiny kicks add up. The envelope rotates faster than it would if the star were alone. That faster rotation could be part of the reason Betelgeuse's pulsations are so irregular compared to other red supergiants. Most red supergiants pulsate in a relatively regular manner, their brightness rising and falling on predictable cycles driven by waves of compression and expansion propagating through the atmosphere. Betelgeuse pulsates too, but its cycles are messy, modulated by that long 6-year period tied to Siwarha's orbit and by shorter, irregular variations that nobody has fully explained. The rotation induced by the binary interaction adds another layer of complexity, distorting the pulsations and making the star's behavior harder to predict. Another piece of the puzzle that the binary models help explain is Betelgeuse's chemical composition. Observations of the star's spectrum show an unusually high abundance of nitrogen compared to what you would expect for a star of its mass and age. Nitrogen is produced in stellar interiors through a process called the CNO cycle, where carbon, nitrogen and oxygen are cycled through a series of fusion reactions that convert hydrogen into helium. The nitrogen gets made as a byproduct and accumulates in the core. For that nitrogen to show up at the surface, it has to be dredged up from the interior by convection or mixing. Single-star models have a hard time explaining the amount of nitrogen seen in Betelgeuse's atmosphere. The mixing should not be efficient enough to bring that much nitrogen to the surface, not this early in the star's evolution, but binary models can explain it. The interaction with Siwarha, the tidal distortions, the angular momentum transfer, the enhanced turbulence in the envelope, all of that increases the mixing efficiency. Material from deep in the star gets stirred upward more effectively than it would in a single star. The nitrogen that was made in the core millions of years ago has had time to work its way to the surface, and now we can see it in the spectrum. That enhanced mixing also means the core is not as chemically stratified as it would be in a single star. In a normal red supergiant, the core is divided into distinct shells, each fusing a different element, with sharp boundaries between them. The innermost region fuses silicon into iron, or if the star has not gotten that far yet, carbon into neon or helium into carbon. Above that is a shell fusing the next lighter element, and above that another shell, like an onion. Each shell operates independently, and the boundaries stay sharp because the mixing between layers is slow. In a binary system, the boundaries blur. Material leaks from one shell to another. Fusion products from deeper layers contaminate the outer shells. The whole structure becomes messier, less orderly, harder to model. For theorists trying to predict what will happen when Betelgeuse finally explodes, this is a nightmare. The properties of the supernova depend critically on the structure of the core at the moment of collapse. How much mass is in the iron core? How much is in the silicon shell? How steep is the density gradient? If you get those details wrong, your predictions for the supernova's brightness, its duration, its spectral features, all of it will be off. The single-star models assumed a clean onion structure. The binary models say that assumption is wrong. The core is messy, and messy cores produce messy supernovae. One of the predictions to come out of the updated binary models is that when Betelgeuse does eventually explode, the supernova might be dimmer and longer-lived than previous estimates suggested. A star with a less massive envelope produces a fainter supernova because there is less material to light up. A star with a disrupted core structure takes longer to collapse because the infalling layers do not hit a clean symmetric core. Instead, they hit a lumpy asymmetric mess, and the rebound is less efficient. The explosion still happens, the core still collapses, a neutron star or black hole still forms, but the light curve, the graph of brightness versus time, looks different. Instead of peaking sharply and then fading over a few months, the peak might be lower and the fade slower, stretched out over a year or more. That difference matters if you are trying to use the supernova as a cosmological distance indicator, or if you are trying to measure the properties of the progenitor star from the explosion. If Betelgeuse goes off and the light curve does not match the models, astronomers will have to go back and figure out what they got wrong. The presence of Siwarha is almost certainly part of that answer. There is also the question of what happens to Siwarha itself. The companion is not going to survive the supernova. When Betelgeuse's core collapses, the explosion will rip through the envelope at a few % of the speed of light, hitting the companion with a wall of radiation and high-velocity gas that will shred it almost instantly. Siwarha will be vaporized, torn apart, its atoms mixed with the expanding debris and scattered into space. By the time the supernova fades and the remnant cools, there will be no trace of the companion left. Just a nebula of glowing gas expanding outward at thousands of kilometers per second, and somewhere in the middle, a neutron star or black hole, the collapsed core of Betelgeuse, spinning silently in the dark. But that is still in the future. For now, Siwarha is still there, still orbiting, still plowing through Betelgeuse's atmosphere every 6 years, leaving its gravitational fingerprints in the velocity data. And astronomers are still working to refine the models to figure out exactly how much the companion has affected Betelgeuse's evolution and how much time the star has left. The answer to that question is not settled. Different research groups, using different assumptions and different modeling techniques, are getting different results. Some models put the remaining lifetime at a few 100,000 years, others put it closer to 1 million. A few outliers, using more aggressive assumptions about mass loss and core evolution, suggest the star could go as soon as 10,000 years from now, though those models are generally considered too extreme. The consensus, if you can call it that, is somewhere in the middle. Betelgeuse probably has a few 100,000 years left, maybe more. Definitely not less than 100,000, unless something we have not accounted for is happening inside the core right now. The discovery of Siwarha did not move the timeline up, it pushed it back. That might sound disappointing if you are hoping to see a supernova in your lifetime. It is not. Because what the discovery really did was show us that Betelgeuse is more interesting, more complicated, and more scientifically valuable than we thought. It is not just a dying star. It is a laboratory for studying binary interactions, mass loss, stellar winds, dynamical friction, and the chaotic final stages of massive stellar evolution. And we are watching it in real time, catching the companion in the act of shaping the supergiant's fate. The old models assumed the death certificate had already been written. Born 20 million years ago, died in 100,000 years. Cause of death: core collapse. Case closed. The new models say we need to rewrite that certificate. Cause of death is still core collapse, but the timing is uncertain. The contributing factors include binary interaction and enhanced mass loss, and the final explosion may not look like the textbook version we were expecting. That uncertainty is not a failure, it is progress. Because now we know what we do not know, and we know what observations we need to make to fill in the gaps. And one of those gaps, one of the biggest, has to do with what is happening in Betelgeuse's core right now. Whether the star is still burning helium or whether it has moved on to carbon. Because that distinction, more than anything else, will determine how much time is left. And figuring out which stage the core is in is harder than it sounds. Figuring out what stage of nuclear fusion a star is in sounds straightforward on paper. You measure the star's brightness, its temperature, its size, maybe its surface composition, if you can get a decent spectrum. Then you compare those measurements to models of stellar evolution, the theoretical roadmaps that describe how stars of different masses burn through their fuel over time. Match the observations to the models and you have your answer. The star is burning hydrogen, or helium, or carbon, or whatever stage fits the data. Easy. Except it is not easy. Not even close. And Betelgeuse, predictably, has spent the last few years demonstrating exactly how badly that process can go wrong when you are dealing with a star that refuses to behave like the textbooks say it should. In early 2023, a team of researchers published a paper that sent a ripple of excitement through the astronomical community and a much larger ripple through the science media outlets that cover astronomy for the general public. The paper, based on detailed analysis of Betelgeuse's pulsations, concluded that the star was likely in the late stages of core carbon burning. Not just carbon burning in general, but late-stage carbon burning, the kind that happens right before the core runs out of fuel, shuts down and collapses. The implications were immediate and dramatic. If Betelgeuse was burning carbon in its core, and if it was near the end of that process, then the remaining lifetime could be measured not in hundreds of thousands of years, but in decades, maybe less. The paper used the phrase tens of years, not centuries, not millennia, tens of years within a human lifetime, possibly within the next few decades. The authors went so far as to suggest that Betelgeuse was a good candidate for the next galactic supernova, the next explosion in our own Milky Way galaxy visible from Earth. That statement, delivered in the dry technical language of an astrophysics preprint, was catnip for headline writers. Within days, articles started appearing with titles like "Betelgeuse could explode in our lifetime" and "Red Supergiant nearing final stage before supernova." Social media picked it up. Reddit threads filled with speculation. Astronomy forums lit up with arguments about whether the claim was credible or overblown. For a few weeks, Betelgeuse was back in the spotlight, and the supernova watch that had quieted down after the Great Dimming was suddenly active again. The problem, and it is a big problem, is that the claim was almost certainly wrong. Not wrong in the sense that the data was bad or the analysis was sloppy. The researchers who published the paper were careful, methodical, and honest about the uncertainties in their work. They were wrong in the sense that they were solving the right problem with the wrong model. They were trying to figure out what Betelgeuse was doing by comparing it to models of single stars evolving in isolation. And Betelgeuse, as we now know, is not a single star. It is part of a binary system. That difference, small as it might sound, changes everything. To understand why the carbon burning claim fell apart, you need to understand what carbon burning actually is and why it matters for predicting when a star will explode. Stellar fusion is a ladder. Each rung burns a different element and releases a different amount of energy. You start at the bottom with hydrogen, the lightest and most abundant element in the universe. Fuse two hydrogen nuclei together and you get helium plus a small burst of energy. That energy, released deep in the core, pushes outward and holds up the weight of the star. As long as the hydrogen keeps burning, the star stays stable. Eventually, the hydrogen in the core runs out. Not the hydrogen in the outer layers, just the core. The core contracts under its own weight, heats up, and if the star is massive enough, it gets hot enough to start fusing helium. 3 helium nuclei fuse into carbon, 4 helium nuclei into oxygen. The energy released is less per reaction than hydrogen fusion, so the star has to burn faster to generate the same outward pressure, but it works. The core stabilizes again, now burning helium instead of hydrogen. When the helium runs out, the core contracts again, heats up again, and if the star is still massive enough, it ignites the next rung, carbon, fusing carbon into heavier elements like neon, sodium, and magnesium. This is where things start moving fast. Hydrogen burning in a star like Betelgeuse lasts a few million years. Helium burning lasts a few 100,000 years, maybe 1,000,000 depending on the star's mass. Carbon burning lasts about 1,000 years, sometimes 1,500 if you are lucky, 1,000 years. That is the entire duration of the carbon-burning phase for a star with 15 to 20 solar masses, from the moment the core lights up and starts fusing carbon to the moment the carbon runs out and the core moves on to the next element. Roughly 1,000 years pass. For comparison, the pyramid at Giza was built about 4,500 years ago. The Roman Empire fell about 1,500 years ago. 1,000 years is not a long time even by human historical standards. On a cosmic timescale, it is an eye blink. After carbon comes neon burning, a few years, then oxygen burning, about a year, then silicon burning, a week, then iron, and iron does not burn. Iron is the end of the line. The moment the core fills with iron, fusion stops. The core collapses, the star explodes. If you know what stage a star is in, you know how much time it has left. A star burning hydrogen has millions of years. A star burning helium has hundreds of thousands. A star burning carbon has 1,000. A star burning silicon has a week. The difference between those stages is the difference between irrelevant and urgent. So when the 2023 paper claimed that Betelgeuse was in late-stage carbon burning, it was claiming that the star had less than 1,000 years left. Possibly much less. The late-stage qualifier suggested the core had already burned through most of its carbon and was approaching the transition to neon burning. If that were true, Betelgeuse could go supernova within a human lifetime, maybe sooner. The claim was not that the star would definitely explode tomorrow. It was that the clock was ticking in human time rather than geological time, and that anyone alive today who planned to live another few decades had a non-zero chance of seeing it happen. That is an extraordinary claim, and extraordinary claims require extraordinary evidence. The evidence in this case came from pulsations. Betelgeuse pulsates. Its size, brightness, and surface velocity oscillate on regular and semi-regular cycles. The main pulsation period is about 400 days. There is also a longer period around 6 years, which we now know is tied to Siwarha's orbit, and a variety of shorter, irregular variations that come and go unpredictably. These pulsations are not random. They are driven by waves of pressure moving through the star's interior, compressing and expanding the outer layers in a rhythmic pattern. By studying the pulsations, you can learn things about the star's internal structure that you cannot measure any other way. The technique is called astrocosmology, the stellar equivalent of using earthquakes to study Earth's interior. When a wave travels through a star, its speed and behavior depend on the density, temperature, and composition of the material it is moving through. A wave moving through a dense core travels differently than a wave moving through a diffused envelope. By measuring how the star's surface moves, how fast it rises and falls, and how those motions change over time, you can build a model of what the interior looks like. You can estimate the size of the core, the thickness of the different layers, and in principle what fuel is burning where. The 2023 team used astrocosmology to model Betelgeuse's pulsations and infer the properties of its core. They built a series of stellar evolution models, each representing a star at a different stage of its life. Some models had cores burning hydrogen. Some had cores burning helium. Some had cores burning carbon. Then they calculated what pulsation periods each model would produce and compared those predictions to the observed pulsations of Betelgeuse. The best match, according to their analysis, came from models where the core was burning carbon, not just starting to burn carbon, but well into the process. The pulsation periods, the surface velocities, the overall behavior of the star, all of it fit better with a carbon-burning core than with a helium-burning core or a hydrogen-burning core. That fit combined with other observations like Betelgeuse's high luminosity and large radius, led them to conclude that the star was likely in late-stage core carbon burning, and from there the timeline followed. If carbon burning lasts about 1,000 years, and if Betelgeuse is already partway through that phase, then the remaining time is less than 1,000 years. How much less depends on how far along the star is, which the models could not pin down precisely. But tens of years was within the plausible range, maybe a century, maybe more, but not hundreds of thousands of years. Not the comfortable buffer that earlier estimates had provided. The paper was careful to note the uncertainties. Stellar models are only as good as the physics you put into them, and there are a lot of things about red supergiant interiors that we do not understand very well. Convection, for example, the churning motions of hot gas rising and cool gas sinking, which transport energy through the star's outer layers and mix material between different regions. Convection is notoriously difficult to model. It depends on turbulence, viscosity, rotation, magnetic fields, all kinds of messy nonlinear effects that do not have clean analytical solutions. Different modeling codes handle convection differently, and the results can vary significantly depending on which assumptions you make. The same is true for mass loss. Red supergiants lose mass through stellar winds, slow, steady streams of gas that blow off the surface and drift into space. The rate of mass loss affects the star's evolution because it changes the total mass of the star over time. Lose too much mass, and the core's evolution speeds up because there is less weight pressing down on it. Lose too little, and the evolution slows down. The 2023 models assumed a particular mass loss rate based on observations of other red supergiants, but Betelgeuse, as we have learned, does not necessarily behave like other red supergiants. Despite those caveats, the paper's conclusion was clear. Betelgeuse was most likely in carbon burning. The timeline to supernova was short, and the star was a prime candidate for the next nearby explosion. The media ran with it. The scientific community was more cautious. Some astronomers pointed out that the same pulsation data could also be fit, almost as well, by models where the core was still burning helium. Helium burning lasts hundreds of thousands of years. If Betelgeuse was in helium burning rather than carbon burning, the timeline was completely different. Not tens of years, not 1,000 years, 100,000 years or more. The difference between urgent and irrelevant. Other researchers noted that Betelgeuse's surface composition, measured from high-resolution spectra, did not show the kind of chemical signatures you would expect from a star in advanced carbon burning. When a star burns carbon in its core, some of the fusion products, elements like neon and magnesium, can get mixed up to the surface by convection. If Betelgeuse was deep into carbon burning, you would expect to see elevated levels of those elements in its atmosphere. You do not. The surface composition looks more consistent with helium burning or possibly early carbon burning at most. Then there was the issue of the pulsations themselves. Betelgeuse's pulsations are not clean and regular the way the pulsations of a single star should be. They are messy, modulated by that 6-year period, interrupted by irregular variations that do not fit any simple pattern. That messiness could be a sign that something other than internal fusion processes is driving the pulsations, something external, something like a companion star. By late 2023, the carbon burning claim was already under fire. A comprehensive review paper, summarizing decades of observations and modeling work on Betelgeuse, concluded that the star was most likely still in core helium burning. Not carbon, helium. The review acknowledged that some models could fit the data with a carbon-burning core, but it argued that those models required a very specific and somewhat contrived set of assumptions. The simpler explanation, The one that required fewer assumptions and fit the broader range of observations was that Betelgeuse was still working its way through helium, with tens or hundreds of thousands of years left before it moved on to carbon. The review was published just as the evidence for Siwarha was starting to solidify. The timing was not coincidental. Once the companion was confirmed, the entire framework for interpreting Betelgeuse's behavior had to be revised. Binary stars do not evolve the same way single stars do. They exchange mass. They transfer angular momentum. They tidally distort each other's shapes and mix material between the core and the envelope more efficiently than convection alone can manage. All of those effects change the pulsation periods, the surface composition, the luminosity, everything you would normally use to infer the star's evolutionary stage. The pulsation models that had pointed to carbon burning were single-star models. They assumed Betelgeuse was evolving in isolation, driven purely by internal processes. The discovery of Siwarha invalidated that assumption. You cannot use a single-star model to interpret the pulsations of a binary system and expect to get the right answer. The companion's gravity, its orbital motion, the drag it experiences as it moves through the envelope, all of that feeds back into the pulsations in ways the models had not accounted for. This is where the carbon-burning claim fell apart, not because the pulsation data was wrong, not because the modeling was sloppy, but because the model itself was incomplete. The researchers who published the 2023 paper were solving the right problem with the wrong tool. They were asking what stage Betelgeuse was in and answering based on the assumption that it was a single star. That assumption, reasonable at the time, turned out to be false. And once the assumption broke, the conclusion built on top of it collapsed. The revised models, the ones that account for Siwarha's presence, tell a very different story. When you include the effects of the companion, the gravitational perturbations, the enhanced mixing, the altered mass loss rate, the pulsation periods that looked like carbon burning start to look more like helium burning with complications. The surface composition, which did not quite fit carbon burning, fits helium burning much better. The long secondary period, which single-star models struggled to explain, is naturally explained by the 6-year orbital period of the companion. Put it all together, and the picture is clear. Betelgeuse is not in late-stage carbon burning. It is not even in early carbon burning. It is still fusing helium in its core, converting helium into carbon and oxygen, releasing energy at a rate that can sustain the star for another 100,000 years or so, maybe more, maybe less. The uncertainties are still large because modeling a binary system is harder than modeling a single star, and because there are aspects of Betelgeuse's internal structure that we still do not understand. But the timeline is not tens of years, it is not 1,000 years, it is long. Comfortably long. Long enough that nobody alive today has any realistic chance of seeing Betelgeuse explode. That revision, from imminent to distant, was not just a tweak to the numbers. It was a fundamental reinterpretation of what Betelgeuse is and how close it is to the end. They applied standard techniques. They reported their results honestly and with appropriate caveats. The lesson is that even careful scientists, using the best tools available, can arrive at the wrong conclusion if they are working with an incomplete picture of reality. And in this case, the incomplete picture was the assumption that Betelgeuse was alone. Binary stars are common. More than half of all stars in the galaxy are part of binary or multiple systems. Yet stellar evolution models, the ones used to predict lifetimes and evolutionary stages and supernova timelines, are almost always single-star models. The reason is simple: single stars are easier to model. Binary stars require you to solve two sets of equations simultaneously, track the interactions between the stars, account for mass transfer and tidal effects and orbital evolution. It is computationally expensive and theoretically complicated. So unless there is clear evidence that a star is part of a binary, the default assumption is to treat it as single. For most stars, that assumption is fine. The companion, if it exists, is far enough away that it does not affect the primary star's evolution in any significant way. For Betelgeuse, the assumption was catastrophically wrong. Siwarha is not far away. It is embedded in the envelope. It is interacting. It is changing the star's behavior in ways that single-star models cannot capture. And because those models could not capture the binary effects, they misread the data. They saw pulsations that looked like carbon burning and concluded the star was near the end, when in fact the pulsations were being distorted by the companion and the star was still in an earlier, much longer-lived phase. The carbon-burning conundrum, then, is not really about carbon burning. It is about models, about assumptions, about the gap between what we think we know and what the universe is actually doing. For decades, astronomers looked at Betelgeuse and saw a textbook red supergiant, a star marching predictably toward an inevitable explosion on a timeline that could be calculated with reasonable confidence. The Great Dimming shook that confidence. The discovery of Siwarha shattered it, and the realization that the carbon-burning claim was built on a flawed model finished the job. We are back to square one. Betelgeuse might explode tomorrow. It almost certainly will not, but the probability is not zero. It might explode in 1,000 years. It might explode in 100,000 years. The honest answer, the one that reflects the current state of knowledge, is that we do not know. The range of plausible timelines is so wide that it spans 5 orders of magnitude. From decades to hundreds of millennia. That is not a prediction, that is an admission of uncertainty. The only way to narrow that range is to figure out what is happening inside the core right now. Not what we think is happening based on models, what is actually happening. And the only way to do that is to listen to the star. To measure the waves propagating through its interior with enough precision that we can map the core's structure directly without relying on models that assume things we now know are not true. That is not easy. It requires instruments that can detect incredibly faint signals buried under layers of noise. It requires years of continuous observation. It requires new techniques that have only recently become practical. But it is possible. And in the last few years, astronomers have started doing exactly that. Listening to Betelgeuse's heartbeat, mapping the seismic waves rippling through its interior, trying to read the star's secrets from the inside out. What they are finding is not what anyone expected. The problem with dying stars is that they do not come with instruction manuals. You cannot crack open the outer layers and look inside. You cannot lower a probe into the core and measure the temperature. You cannot take a sample of the fusion zone and analyze it in a lab. All you can do is stand at a safe distance, billions of kilometers away, point your instruments at a glowing ball of plasma, and try to figure out what is happening underneath based on the faint signals leaking out. For most of astronomy's history, that was not good enough. Observing a star meant watching its surface, how bright it was, what color, whether it flickered or pulsed or stayed steady. That is it. The interior, the core where the real action happened, was a black box. You could build theoretical models, run simulations, make educated guesses, but you could not actually see inside. The core was hidden behind hundreds of thousands of kilometers of opaque gas, and there was no way around that. Then in the 1960s, astronomers realized they had been sitting on the answer all along. The stars were already telling them what their interiors looked like. They just had not been listening closely enough. The discovery came from studying the sun. In the early 60s, a researcher named Robert Layton at Caltech noticed something odd while analyzing images of the solar surface. The surface was moving. Not just the usual convection, the boiling turbulence you see when you watch high-resolution solar footage. This was different. The entire surface was oscillating, rising and falling in a slow rhythmic pattern with a period of about 5 minutes. Up and down, over and over, covering the entire visible disk. At first, Leighton thought it might be a calibration error. Maybe his instrument was drifting. Maybe the atmospheric seeing was playing tricks. But the signal was too clean, too regular. The oscillations were real. The sun was ringing like a bell, not a sharp metallic ring, but a deep, slow thrumming, the kind you feel in your chest when you stand next to a large speaker. Within a few years, other researchers confirmed the discovery and started mapping out the details. The sun was not just oscillating at one frequency, it was oscillating at thousands of frequencies simultaneously, each corresponding to a different mode of vibration. Some modes made the entire surface expand and contract uniformly, like a balloon inflating and deflating. Other modes created patterns of waves rippling across the surface, bright ridges and dark troughs moving in precise geometric arrangements. The sun's surface looked like the surface of a pond after you have dropped a handful of pebbles into it. Waves everywhere, interfering, reinforcing, creating a complex shifting pattern that never quite repeated. Those waves were not random. They were the result of sound waves, pressure waves, propagating through the sun's interior. Deep inside the sun, turbulence and convection were constantly generating noise, acoustic vibrations that bounced around the interior like echoes in a canyon. Most of those waves got absorbed or scattered, but some of them, the ones with just the right frequency and geometry, could travel all the way from the core to the surface and back down again, trapped in a resonant cavity by the density gradient inside the star. Those resonant waves built up over time, reinforcing themselves, creating standing wave patterns that persisted for days or weeks. And when those waves reached the surface, they pushed the photosphere up and down, creating the oscillations Leighton had seen. The analogy everyone uses, because it is actually pretty accurate, is a musical instrument. When you pluck a guitar string, it vibrates at a specific frequency determined by the string's length, tension, and mass. If you change the length by pressing down on a fret, the frequency changes, the note changes. The same principle applies to sound waves bouncing around inside a star. The frequency of the wave depends on the properties of the material it is traveling through, how dense the gas is, how hot it is, what it is made of. If you can measure the frequencies of all the waves bouncing around inside a star, you can work backward and figure out the density, temperature, and composition at every depth. You can map the interior. The field that grew out of this realization is called helioseismology, the study of the sun's interior using its oscillations. The name is a deliberate parallel to seismology, the study of Earth's interior using earthquakes. Both fields work the same way. Waves propagate through a medium. You measure how the waves behave at the surface. You use that information to infer what the interior looks like. For Earth, the waves are seismic waves from earthquakes. For the sun, the waves are acoustic waves from convective turbulence. Different medium, same principle. Helioseismology transformed solar physics. Before the oscillations were understood, the sun's interior was mostly guesswork. Models predicted that the core should be hot enough to fuse hydrogen, about 15 million degrees, and dense enough to sustain the fusion reactions, about 150 times the density of water, but nobody knew for sure. The models made assumptions about how energy was transported through the interior, about how the temperature and density changed with depth, about what the composition was. Those assumptions could be wrong. There was no way to test them directly. The oscillations provided the test. by measuring thousands of individual oscillation modes and comparing them to theoretical predictions. Helioseismologists were able to map the Sun's interior in exquisite detail. The temperature profile, the density profile, the sound speed at every depth, all of it matched the models almost perfectly. The Sun's core was right where the models said it should be, at the right temperature, at the right density. The predictions held up. The physics worked. More importantly, helioseismology revealed features the models had missed. The boundary between the radiative core and the convective envelope, called the tachocline, turned out to be much thinner and sharper than anyone expected. The rotation rate inside the Sun varied with depth in ways that were completely unanticipated. The oscillation data even detected large-scale flows circulating through the convective zone, currents of plasma moving from the equator to the poles and back, invisible from the surface but clearly present in the wave patterns. All of that came from measuring how the surface moved, up and down, a few hundred meters per second at most. Tiny motions but packed with information. And once helioseismology proved itself on the Sun, the obvious next step was to try it on other stars. That is harder, much harder. The Sun is close. We can resolve its surface. We can watch individual oscillation modes play out in real time, tracking how different parts of the disk move at different speeds and in different directions. Other stars are too far away for that. They are points of light. You cannot see their surfaces. You cannot watch the waves ripple across them. All you can measure is the integrated light from the entire star, the sum of contributions from every part of the disk blurred together into a single brightness measurement or a single spectral line. But that turns out to be enough, because the oscillations, even when you cannot resolve them spatially, still show up as variations in the star's brightness and in the Doppler shifts of its spectral lines. When a wave pushes part of the surface outward, the star gets slightly brighter, and the light from that region shifts toward the blue because it is moving toward you. When the wave pulls the surface inward, the star dims slightly, and the light shifts toward the red. Those variations are tiny, fractions of a percent in brightness, meters per second in velocity, but modern instruments can detect them. Photometers sensitive enough to measure brightness changes of a few parts per million. Spectrographs with velocity precision down to a meter per second or better. If you point those instruments at a star and watch it for long enough, the oscillations show up in the data as periodic signals, peaks in the frequency spectrum that correspond to the star's internal vibration modes. The field is called astroseismology, the stellar version of helioseismology. Same technique, different targets, and Betelgeuse, it turns out, is one of the best targets in the sky. Not because it is close, though at 700 light-years it is relatively nearby for a red supergiant. Not because it is stable, because it very much is not. But because it is large, because it is bright, and because it oscillates with modes that are strong enough to detect from Earth even through all the noise and chaos of its atmosphere. Betelgeuse has been oscillating as long as anyone has been watching it. The main pulsation period, about 400 to 425 days, has been known since the 19th century when astronomers first started logging regular brightness measurements. That slow rise and fall in luminosity, visible even to the naked eye if you watch the star over the course of a year, is driven by a radial oscillation mode, the entire star expanding and contracting, swelling up and shrinking back down, like a balloon being inflated and deflated. When the star expands, the surface area increases, the temperature drops slightly, and the brightness changes. When it contracts, the opposite happens. The result is a periodic variation in brightness that repeats roughly once every 14 months. That radial mode is useful for astroseismology because it is simple. It affects the entire star uniformly, so the signal is strong and relatively easy to model, but it only tells you one thing about the interior: how long it takes for a pressure wave to travel from the core to the surface and back. That is valuable, but it is not enough to map the star's internal structure in detail. For that, you need more modes. You need to measure oscillations at different frequencies, different geometries, different penetration depths. The more modes you can detect, the more information you have, and the better you can constrain what the interior looks like. Betelgeuse has plenty of modes. The 400-day period is just the loudest. Beneath it, buried under layers of noise and variability, there are shorter periods, around 100 to 180 days, corresponding to higher-order radial modes or possibly non-radial modes, where different parts of the surface move in opposite directions. There is the long 6-year period tied to Siwarha's orbit, which is not really an internal oscillation but still shows up in the data as a modulation of the shorter periods. And there are irregular variations, flickering on timescales of days to weeks, driven by convection and turbulence and the chaotic churning of the star's outer envelope. For years, teasing those signals apart was nearly impossible. The data was too noisy, the oscillations were too irregular. Betelgeuse is not a well-behaved star. It does not pulsate like a metronome the way some variable stars do. It drifts. The periods change slightly from cycle to cycle. The amplitudes vary. Sometimes a mode that showed up clearly in one year's data would disappear the next year, swamped by some other process. Astrocosmology works best on stars that oscillate cleanly and predictably. Betelgeuse oscillates like a drunk orchestra warming up. But over the last decade, the data has gotten better, a lot better. Space telescopes, ground-based interferometers, high-precision spectrographs, adaptive optics systems that can correct for atmospheric turbulence in real time. All of those tools have been pointed at Betelgeuse, some of them continuously for months or years at a time, building up datasets rich enough and clean enough that the oscillation modes start to emerge from the noise. One of the key breakthroughs came from combining different types of observations. Photometry, the measurement of brightness over time, gives you one piece of the puzzle. Spectroscopy, the measurement of velocity through Doppler shifts, gives you another. Interferometry, which maps the star's surface geometry, gives you a third. Each technique is sensitive to different aspects of the oscillations. Photometry picks up the brightness changes caused by temperature variations and changes in surface area. Spectroscopy picks up the velocity changes caused by the surface moving toward or away from you. Interferometry picks up the spatial structure, whether the whole star is moving uniformly or whether different parts are moving in opposite directions. Put them together and you start to see the full picture. The 420-day mode, for example, shows up clearly in both photometry and spectroscopy with the same period, confirming that it is a radial mode affecting the entire star. The shorter periods, around 150 days, show up more strongly in velocity measurements than in brightness, suggesting they might be non-radial modes where the velocity signal is larger than the brightness signal because the compression and expansion in different regions partly cancel each other out when you integrate over the whole disk. The longest period, the 6-year cycle, shows up in everything: brightness, velocity, even in high-resolution images of the star's surface. That is because it is not purely an internal oscillation. It is the companion, Siwarha, passing through the atmosphere every 6 years, compresses gas, triggers instabilities, and sets off waves that propagate through the envelope and eventually reach the surface. Those waves modulate the shorter period oscillations, sometimes amplifying them, sometimes damping them, creating the irregular beating pattern that makes Betelgeuse's pulsations so hard to model. One of the most detailed asteroseismic studies of Betelgeuse was published in 2022 using data from the Atacama Large Millimeter Array, ALMA, combined with archival photometry and spectroscopy spanning more than a decade. ALMA, sitting on a high plateau in the Chilean desert, is an array of 66 radio dishes that work together to form a single instrument with a resolution sharp enough to resolve the surface of Betelgeuse at millimeter wavelengths. At those wavelengths, the star's emission comes from the cooler outer layers of the atmosphere, a few thousand kilometers above the visible photosphere. By watching how those layers move over time, ALMA can measure the velocity structure of the atmosphere with a precision that optical telescopes cannot match. The ALMA data showed that Betelgeuse's surface is not moving uniformly. Different regions of the star are moving at different speeds and in different directions, a clear signature of non-radial oscillations and large-scale convection. The northern hemisphere and the southern hemisphere sometimes move in opposite directions, one expanding while the other contracts. The equatorial region and the polar region show different velocity patterns, possibly related to the star's rotation. And overlaid on all of that is the regular 400-day pulse, the deep, slow breathing of the entire envelope, expanding and contracting in unison. By analyzing the ALMA velocity maps alongside the photometric light curves and the spectroscopic line profiles, the research team was able to identify at least 5 distinct oscillation modes: the dominant 420-day radial mode, a shorter 180-day mode, possibly the first overtone of the radial oscillation, a roughly 400-day mode with a different spatial pattern, likely a non-radial mode, where parts of the surface move out of phase with each other, and 2 longer modes, one around 1,000 days and one around 2,000 days, both of which appear to be related to large-scale convective overturn in the outer envelope rather than purely acoustic oscillations. Each of those modes carries information about a different region of the star's interior. The 400-day radial mode probes the deep envelope and possibly the boundary between the envelope and the core. The shorter overtone modes sample the middle and outer envelope where the density drops and the sound speed changes. The long convective modes tell you about the turnover time of the largest convection cells, the giant plumes of hot gas rising from below and cool gas sinking back down. Put it all together and you start to build a 3-dimensional picture of what Betelgeuse looks like on the inside. The picture that emerges is messy, messier than the Sun, messier than most other stars. Betelgeuse's interior is not neatly stratified into clean layers. It is turbulent, chaotic, constantly churning. The convection in the outer envelope is not a smooth background process. It is violent. Individual convection cells, blobs of rising hot gas, can be hundreds of millions of kilometers across, larger than the orbit of Mars. Those cells rise slowly, over the course of months or years, carrying energy from the interior toward the surface. When they reach the photosphere, they release their heat, cool, and sink back down, creating a circulation pattern that constantly redistributes material throughout the envelope. That convection is what drives a lot of the irregular variability in Betelgeuse's brightness and velocity. When a particularly large or hot cell reaches the surface, it creates a bright spot, a region that glows more intensely than the surrounding photosphere. When a cool-down flow reaches the surface, it creates a dark spot, a region that appears dimmer. The surface is covered with these spots, constantly appearing, evolving and disappearing as the convection cells cycle through. High-resolution images from interferometers like the Very Large Telescope's Matisse instrument show the spots clearly, bright and dark patches spread across the disk, shifting and changing from one observation to the next. The convection also generates the shock waves that can trigger mass ejection events like the Great Dimming. When a rising plume reaches the photosphere, it does not just stop. It keeps going, punching through the surface and launching material into space. Most of the time, those punches are weak, barely disturbing the atmosphere. Every so often, though, a particularly energetic plume hits the surface at just the right moment, when the envelope is already extended from a pulsation cycle, when the companion is nearby stirring up the gas, and the shock wave that results is strong enough to eject a significant mass of material. Astroseismology is starting to constrain when and how those ejections happen. By mapping the oscillation modes and tracking how they change over time, researchers can identify periods when the star's envelope is more extended, when the surface gravity is weaker, when the conditions are ripe for a mass loss event. Those periods correlate with the minima of the long pulsation cycles. When the 400-day cycle and the 6-year cycle both hit their low points at the same time, the star is at its largest and most unstable. That is when ejections are most likely. That is what happened in 2019. The cycles lined up, a convective plume hit the surface, and Betelgeuse blew its top. But astroseismology does more than just predict surface behavior. It probes the core. The deep interior where fusion is happening, where the star's fate is being decided. The oscillation modes that penetrate all the way to the core are sensitive to the core's size, its density, its temperature, and critically, what fuel is burning there. A core burning hydrogen produces a different internal structure than a core burning helium. Helium burning produces a different structure than carbon burning. The sound speed changes. The density gradient changes. And those changes show up in the oscillation frequencies. This is where the astroseismic data becomes crucial for answering the question of when Betelgeuse will explode. The old models, the ones that assumed a single star evolving in isolation, used the oscillation frequencies to argue that Betelgeuse was burning carbon. The frequencies seemed to fit better with carbon-burning models than with helium-burning models. But those models did not account for the companion. They did not account for the enhanced mixing, the altered mass loss rate, the gravitational perturbations from Siwarha. Once you add those effects into the models, the frequency fits change. The modes that looked like carbon burning start to look more like helium burning with complications. The latest astroseismic models, published in late 2024 and early 2025, incorporate the binary interaction. They model Betelgeuse as a red supergiant with a companion embedded in its envelope, track how the companion's gravity affects the density and velocity structure, and then calculate what oscillation frequencies that system should produce. When you do that, the predicted frequencies match the observed frequencies much better for a helium-burning core than for a carbon-burning core. The fit is not perfect. There are still discrepancies, modes that do not quite line up, suggesting there are aspects of the star's interior that the models have not captured yet. But the overall agreement is good enough to rule out late-stage carbon burning. Betelgeuse is not near the end. It is in the middle, working its way through helium, with tens or hundreds of thousands of years left before it moves on to the next stage. That conclusion is supported by spectroscopy. High-resolution spectra of Betelgeuse's surface, taken with instruments like the ultraviolet and visual Echelle spectrograph on the Very Large Telescope, show the chemical fingerprints of the elements present in the star's atmosphere. Hydrogen, helium, carbon, nitrogen, oxygen, a whole periodic table's worth of elements in various ionization states. The abundances of those elements tell you what has been going on inside the star. Elements like nitrogen, which are produced in the core through the CNO cycle and then dredged up to the surface by convection, are present in higher abundances than you would expect for a star that has not yet burned much of its core fuel. That suggests the core has been active for a while, fusing hydrogen and helium, producing nitrogen and other byproducts, and mixing them up to the surface. but the abundances do not match what you would see in a star that has been burning carbon for a long time. Carbon burning produces elements like neon, sodium, and magnesium. If Betelgeuse had been in carbon burning for hundreds of years, those elements should show up in elevated amounts in the atmosphere. They do not. The surface composition looks more consistent with helium burning, possibly with some early carbon burning mixed in, but not late-stage carbon burning. The spectroscopic evidence, combined with the astroseismic evidence, points in the same direction. Helium core, long timeline, no imminent explosion. High-resolution imaging adds another layer of confirmation. Interferometers like METIS and the Navy Precision Optical Interferometer, NPOI, have mapped Betelgeuse's surface at resolutions high enough to see individual convection cells and track how they move over time. Those maps show that the surface is covered with bright spots and dark spots. Temperature variations of a few hundred degrees spread across the disk in an irregular pattern. The spots are not static, they evolve, merge, split apart, and disappear over the course of weeks to months. That behavior is exactly what you would expect from large-scale convection in the outer envelope, consistent with a star in helium burning, where the envelope is bloated and turbulent but the core is still stable. What the maps do not show is the kind of rapid, dramatic changes you would expect from a star on the verge of core collapse. Stars in the final stages before supernova, the ones burning silicon or iron, tend to develop strong asymmetries in their outer layers, driven by instabilities in the core and by the rapid contraction of the envelope. The surface becomes lopsided. Bright spots appear and disappear on timescales of days or hours rather than weeks or months. The oscillation modes shift erratically as the internal structure changes. None of that is happening with Betelgeuse. The surface is turbulent, yes, but the turbulence is consistent with normal convective behavior, not with pre-supernova instability. One of the most ambitious observational campaigns focused on Betelgeuse started in late 2023 and is still ongoing. A collaboration involving the Hubble Space Telescope, ALMA, the Very Large Telescope, and several smaller ground-based observatories, all coordinating their observations to monitor the star continuously for multiple pulsation cycles. The goal is to catch the star in the act of ejecting material, to watch a surface mass ejection event from start to finish, and to use the combined data from all the instruments to map what happens inside the star when the ejection occurs. The campaign has already produced preliminary results. During one pulsation cycle in early 2024, ALMA detected a strong velocity pulse in the star's atmosphere, a sudden upward surge of gas moving at several kilometers per second. A few weeks later, Hubble saw the southern hemisphere of the star dim slightly, suggesting a dust cloud had formed. The Very Large Telescope, watching in the infrared, confirmed that the southern hemisphere had cooled, consistent with ejected gas condensing into dust grains. The entire sequence from velocity pulse to dust cloud to dimming played out over the course of a few months, and the instruments caught it at every stage. That event was much smaller than the Great Dimming. The brightness drop was only about 5%, barely noticeable to the naked eye, but it was the same kind of process, driven by the same mechanisms. A convective plume, a shock wave, an ejection, a dust cloud. And the fact that the instruments were able to track the event in real time, watching the gas move and the cloud form and the light dim, means we now have a detailed observational record of how Betelgeuse loses mass, not a model, not a simulation, direct observations of the star tearing pieces of itself off and flinging them into space. The astroseismic data from that campaign is still being analyzed. The oscillation modes during the ejection event were different from the modes before and after. The frequencies shifted slightly, the amplitudes changed. Some modes that had been weak became strong, and some that had been strong faded. Those shifts are clues. They tell you how the ejection affected the star's internal structure, how much mass was lost from the envelope, how quickly the star recovered. Put enough of those clues together, and you can start to build a timeline, not just of when the star will explode, but of how it is evolving right now, in real time, cycle by cycle, ejection by ejection. What all of this boils down to is a simple but profound shift in how we study Betelgeuse. For most of the star's observational history, we watched it from the outside. We measured its brightness, its color, its spectrum, all surface properties. That told us a lot, but it left the interior a mystery. We could guess what was happening inside based on models, but we could not see it. Astroseismology changed that. Now we can listen to the star. We can hear the waves bouncing around inside it. We can measure the echoes, decode the signals, and map the interior directly. The core is no longer a black box. It is a target, and every oscillation mode we detect, every frequency we measure, every velocity map we build, brings us closer to understanding what is actually happening down there where the fusion is. The timeline to supernova is still uncertain. The range is still wide, but the uncertainty is shrinking. Not because we are guessing better, but because we are measuring better. Astroseismology, combined with spectroscopy and high-resolution imaging and continuous monitoring, is giving us the tools to finally answer the question we have been asking for decades. How much time does Betelgeuse have left? The answer is not tomorrow. It is not 1,000 years. It is somewhere in between. And with every new dataset, every new oscillation mode, every new observation, that range narrows. We are closing in on the truth. And the truth, as always, is more complicated and more interesting than the simple stories we started with. The tools are getting better. That is the thread running through everything we have learned about Betelgeuse over the last few years. Not that the star is behaving differently, but that we can finally see what it was doing all along. The Great Dimming was not the first time Betelgeuse ejected a massive dust cloud. It was the first time we had the instruments sensitive enough and the observational cadence tight enough to catch it happening in real time. The discovery of Siwarha was not a sudden appearance of a companion star. It was the culmination of decades of velocity measurements finally analyzed with enough care and enough computing power to pull the signal out of the noise. The asteroseismic mapping of the interior was not a breakthrough in the star's behavior. It was a breakthrough in how we listen. And the tools are about to get a lot better. 2027 is not a magic year. Betelgeuse will not suddenly do something it has not been doing for the last 100,000 years. But 2027 marks the beginning of a new generation of observational campaigns, instruments coming online, collaborations forming, and telescope time being allocated to a star that has spent the last half-decade proving it is worth the attention. Some of those campaigns have been in the planning stages since before the Great Dimming. Others were hastily assembled in response to it, cobbled together from existing proposals and redirected funding once it became clear that Betelgeuse was not just interesting, but urgently interesting in ways nobody had anticipated. The first major campaign launches in early 2027 with the James Webb Space Telescope. Webb has already observed Betelgeuse, brief snapshots during its first few years of operation, mostly focused on measuring the dust cloud's composition and tracking how it dispersed. The 2027 program is different. It is a dedicated multi-cycle effort, hundreds of hours of telescope time spread across 2 years, designed to do what Webb does best: map the infrared emission from Betelgeuse's extended atmosphere in exquisite detail, resolve the structure of the dust and gas surrounding the star, and track how material flows outward from the photosphere into the interstellar medium. Webb sees infrared. That matters because most of the action in Betelgeuse's outer envelope happens at wavelengths longer than visible light. The dust grains that formed during the Great Dimming radiate primarily in the mid-infrared, glowing with the heat they absorbed from the star and re-emitting it at wavelengths between 5 and 30 microns. The gas in the extended atmosphere, the region a few stellar radii above the photosphere where the density has dropped but the temperature is still high enough to excite molecules, emits in the near-infrared, producing spectral lines from water vapor, carbon monoxide, and other simple molecules that cannot survive closer to the surface. Ground-based telescopes can see some of that. ALMA, working in the millimeter range, picks up the cool outer layers. Optical telescopes catch the photosphere, but the mid-infrared, the wavelength range where the dust dominates and where the molecular emission is strongest, is blocked by Earth's atmosphere. Water vapor in the air absorbs most of the signal before it reaches the ground. You need a space telescope to see it clearly. And Webb, sitting at the second Lagrange point 1.5 million kilometers from Earth, has the clearest view in the solar system. The 2027 Webb program will map Betelgeuse's dust shell in 3 dimensions, not just a flat image, but a reconstruction of the density and temperature at every point in the surrounding cloud, built up from spectroscopic observations taken at dozens of different wavelengths. That map will show where the dust formed, how it moves, how it cools as it drifts outward, and where it eventually dissipates into the background interstellar medium. By comparing maps taken months apart, the team will be able to measure the velocity of the outflowing material directly, tracking individual clumps as they travel away from the star. That velocity data feeds directly into models of how Betelgeuse loses mass. Right now, the mass loss rate is estimated from the total amount of dust and gas detected around the star, combined with assumptions about how long that material has been accumulating. But those assumptions are shaky. If the dust forms quickly and disperses slowly, the mass loss rate is lower than it looks. If the dust forms slowly and disperses quickly, the rate is higher. Webb will remove the assumptions. By watching the material move in real time, you can calculate the mass loss rate directly. How much material is leaving the star per year, per month, per orbital period of the companion? How much of that material is in the form of dust versus gas? How much of the mass loss happens continuously through a steady wind versus episodically through ejection events like the Great Dimming? Those numbers matter because they determine how long Betelgeuse will stay a red supergiant and how much mass it will have left when the core finally collapses. Lose mass too slowly and the envelope stays bloated, the core stays insulated, and the star lives longer. Lose mass too quickly and the envelope gets stripped away faster than expected, exposing the hotter inner layers and potentially altering the timeline. The difference between a mass loss rate of 10 to the minus 6 solar masses per year and 10 to the minus 5 solar masses per year is an order of magnitude in how much material leaves the star over the next 100,000 years. Webb will pin that number down. The second major campaign is already running and will intensify through 2027 and beyond. The Very Large Telescope Interferometer in Chile, specifically the Gravity and Matisse instruments, has been observing Betelgeuse on and off since 2019. Gravity works in the near-infrared, combining light from 4 8.2-meter telescopes to achieve a resolution equivalent to a telescope more than 100 meters across. Matisse works in the mid-infrared with similar resolution but at longer wavelengths where the dust emission is stronger. Together, they can resolve features on Betelgeuse's surface smaller than a single stellar radius. watching convection cells rise and fall, tracking how the companion's wake moves through the atmosphere, mapping the temperature and density structure in unprecedented detail. The 2027 Gravity program includes a new capability, astrometry, precise measurement of where the star's center of light is located in the sky. Betelgeuse's center of light wobbles, not because the star is moving through space, although it is, but because the surface is asymmetric. Bright spots and dark spots shift the balance of light, making the apparent position of the star drift back and forth by a few milliarseconds. That wobble contains information about what is happening on the surface. When a particularly bright convection cell reaches the photosphere, the center of light shifts toward that cell. When the cell cools and sinks, the center shifts back. By measuring that wobble over multiple pulsation cycles, you can track the evolution of individual convection cells, watching them appear, brighten, dim, and disappear. But there is another wobble buried in the data, the gravitational tug from Siwarha. The companion is massive enough and close enough that its gravity pulls on Betelgeuse's center of mass, causing the supergiant to orbit slightly around the system's common center of gravity. That orbital motion is tiny, a few milliarseconds at most, but it is regular. It repeats every 6 years, synchronized with the companion's orbit. Gravity's astrometry is precise enough to detect it. By measuring the wobble and comparing it to the velocity measurements from spectroscopy, the team will be able to calculate Siwarha's mass directly, not from models, not from assumptions about stellar evolution, but from the dynamics of the orbit. Newton's laws applied to a binary system: mass times distance equals force. Measure the force, measure the distance, get the mass. That mass, once nailed down, will constrain the companion's future. If Siwarha is on the low end of the mass range, closer to one solar mass, it might survive long enough to escape Betelgeuse's envelope before the supergiant explodes. Low-mass stars are denser, more compact, better at resisting tidal disruption. A one-solar mass companion embedded in a red supergiant's atmosphere would lose mass through ablation, gas stripped away by the drag and the radiation pressure, but it might hold together long enough for Betelgeuse's envelope to thin out as the star evolves toward the later stages. At that point, the companion would find itself orbiting outside the envelope again, battered but intact, a survivor of the most hostile stellar environment imaginable. If Siwarha is on the high end, closer to two solar masses, it will not make it. Higher mass stars are larger, puffier, more vulnerable to tidal forces. A two-solar mass companion embedded in Betelgeuse's envelope is already being stretched by tides, its outer layers pulled toward the supergiant by the difference in gravitational pull between the near side and the far side. Those tides will get stronger as the companion spirals inward. Eventually, the tidal forces will exceed the companion's own gravity, and the star will be torn apart. Not in a dramatic explosion, but in a slow unraveling. The outer layers will peel away, spiraling into Betelgeuse's atmosphere, while the core, if it is dense enough, might survive as a naked helium star or a white dwarf precursor, a remnant orbiting deep inside the supergiant until the final explosion vaporizes it. The astrometric data will tell us which scenario is more likely. And that matters not just for Betelgeuse, but for understanding binary evolution in general. Most massive stars are part of binaries. Most of them interact at some point during their lives, exchanging mass, merging, or disrupting each other. Betelgeuse and Siwarha are giving us a front-row seat to that process, a chance to watch a binary system in the act of self-destructing over timescales short enough that we can actually see the changes. The third major campaign is less about new instruments and more about sheer persistence. The Vera the 100th. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, began full survey operations in 2025. Rubin's job is to photograph the entire visible sky every few nights, cataloging everything that changes: supernovae, asteroids, variable stars, transient events that flicker into existence and disappear before most telescopes can follow up. Betelgeuse is not a transient. It is a permanent fixture in Orion, bright enough that Rubin will catch it in every single image that includes that part of the sky. Over the course of a decade, Rubin will accumulate tens of thousands of individual brightness measurements of Betelgeuse, building a light curve with a density and precision that no previous survey has ever achieved. That light curve will capture every pulsation cycle, every convective event, every dust cloud, every interaction with the companion. The 400-day cycle will show up as a smooth sinusoidal wave. The 6-year cycle will modulate that wave, creating the beating pattern we have seen in historical data. And buried underneath, in the noise, there will be shorter irregular variations, flickers and dips that last days or weeks, driven by individual convection cells or transient shock waves. Rubin will catch all of it. And because Rubin is automated, because it observes the entire sky without human intervention, it will catch things that targeted observations miss, outbursts that happen between scheduled telescope runs, brief dips in brightness that last only a few days, events that we did not know to look for because they had never been seen before. One of the key goals of the Rubin program is to identify precursor events, signs that a star is approaching the final stages before supernova. For stars like Betelgeuse, those precursors are not well understood. Theory suggests that as a star burns through the final stages of fusion, the core contracts and heats up, driving instabilities in the overlying envelope. Those instabilities might produce bursts of mass loss, sudden changes in brightness, or shifts in the pulsation periods. But we have never seen those precursors directly because we have never caught a red supergiant in the act of transitioning from a stable phase to the final collapse. Most supernovae come as surprises. The progenitor star looks normal in archival images, sitting quietly in a galaxy millions of light years away, and then one night it explodes. By the time we point our telescopes at it, the star is already gone, replaced by an expanding fireball. Betelgeuse is close enough that we will not miss the precursors. If the star starts doing something unusual, if the pulsations shift, if the mass loss rate spikes, if the surface develops strong asymmetries that persist for months rather than weeks, Rubin will see it. The alert system will flag it. Observatories around the world will follow up. And we will know, possibly years in advance, that something is happening, that the clock is ticking faster than the models predicted, that we just might be entering the final countdown. That is the dream scenario. The one every astronomer working on Betelgeuse secretly hopes for, even if they will not say it out loud because hoping for a star to explode sounds a little ghoulish. The nightmare scenario is the opposite. That Betelgeuse stays stable for another 100,000 years, pulsing and shedding mass and doing exactly what the updated models predict, and nobody alive today will see anything more dramatic than another Great Dimming or two. That is the more likely outcome. That is what the evidence says. But the tools are good enough now that if the unlikely happens, if Betelgeuse defies the odds and enters the final stages within the next few decades, we will catch it, we will see it coming, and we will have time to prepare. Preparation in this context means pointing every available instrument at Orion. Webb, ALMA, the Very Large Telescope, the Extremely Large Telescope when it comes online in the late 2020s, Hubble if it is still operational, ground-based photometers, spectrographs, interferometers, everything. Betelgeuse going supernova would instantly become the most important astronomical event in human history. Not the most energetic, that honor goes to gamma-ray bursts and quasars billions of light-years away. Not the most scientifically surprising, we know supernovae happen and we understand the basic physics, but the most important in terms of sheer observational value. A supernova at 700 light-years, close enough to resolve the expanding shock wave, close enough to measure the chemical composition of the ejector in real time, close enough to detect neutrinos by the thousands and possibly gravitational waves if the core collapse is asymmetric. That is a once-in-a-civilization event. The last time a supernova this close was visible from Earth was 1604, Kepler's supernova, and that one was 10,000 light-years away. The last time a supernova occurred within 1,000 light-years of Earth and left detailed observational records was 1087 SN 1987A in the Large Magellanic Cloud, which is technically outside the Milky Way but close enough that we caught the neutrino burst. Betelgeuse would be closer than either of those by a factor of 10 or more. The neutrino detectors are already waiting. Super Kamiokande in Japan, a tank containing 50,000 tons of ultra-pure water buried under a mountain, watched by thousands of photomultiplier tubes designed to catch the faint flashes of light produced when a neutrino hits a water molecule. Ice Cube in Antarctica, a cubic kilometer of ice instrumented with sensors doing the same thing on a larger scale. Detectors in Italy, in Canada, in China, all of them online, all of them monitoring the sky, all of them configured to send alerts the moment they see a sudden burst of neutrinos from a specific direction. The neutrinos from a supernova arrive hours before the light. They are produced in the core during the collapse, when the protons and electrons are crushed together into neutrons and the excess energy escapes as neutrinos. Those neutrinos travel at nearly the speed of light and pass through the star's outer layers as if they are not there. The light, meanwhile, has to fight its way out, scattering and absorbing and re-emitting over and over as it climbs through thousands of kilometers of opaque gas. By the time the light reaches the surface and starts propagating freely through space, the neutrinos are already halfway to Earth. If Betelgeuse collapses tomorrow, Super Kamiokande would see the neutrino burst first. A sudden spike in the count rate, dozens or hundreds of neutrino interactions over the course of a few seconds, all coming from the direction of Orion. The alert would go out within minutes. Automated systems would send messages to observatories, flagging Betelgeuse as a potential supernova candidate. Telescopes in the southern hemisphere, where Orion is visible during their night, would swing into action immediately. Northern hemisphere observatories would pick it up a few hours later as the Earth rotated and Orion rose above the horizon. Within a day, every major telescope on the planet and in space would be pointed at the same star, watching the light curve rise, recording spectra, measuring velocities, tracking the shock wave as it ripped through the star's outer envelope. The light curve of a Betelgeuse supernova would not be a simple smooth rise and fall. It would be messy, shaped by the structure of the envelope and the asymmetries introduced by the companion. The initial brightening would be fast, a few days to go from normal brightness to outshining every star in the sky. At peak, Betelgeuse would reach an apparent magnitude of around -12 or 13, roughly as bright as the half-moon, but concentrated in a single point of light. You could read by it. You could see it in broad daylight. It would cast shadows at midnight. Orion's shoulder would glow like a second moon for weeks, maybe months, slowly fading as the expanding debris cloud cooled and the radioactive decay of nickel-56, the isotope produced in the supernova that powers the light curve during the decline phase, ran its course. After a year, the light curve would drop below naked eye visibility. After 10 years, you would need a telescope to see it. But the nebula, the glowing cloud of ejected material, would be visible for thousands of years. A new feature in Orion, expanding outward at thousands of kilometers per second, eventually spanning several degrees across the sky. The Crab Nebula, the remnant of the 1054 supernova, is 6 light-years across today, nearly 1,000 years after the explosion. Betelgeuse's remnant would grow even larger because the progenitor star is more massive and the explosion more energetic. In 10,000 years, it would be one of the largest and brightest nebulae in the sky, a testament to the violent death of the star that used to mark the hunter's shoulder. But that is still speculation. Betelgeuse has not exploded. The current best estimates, the ones that incorporate the binary interaction and the asteroseismic constraints and the refined mass loss rates from Webb and ALMA, put the remaining lifetime at somewhere between 100,000 and 300,000 years. The uncertainty is large. The models are not perfect. There are processes inside the star that we do not fully understand, mixing mechanisms that could speed up or slow down the core's evolution, mass loss events that could strip away more of the envelope than expected. But the central conclusion is robust. Betelgeuse is not in the final stages, it is in the middle. Still burning helium, still stable, still tens of thousands of pulsation cycles away from running out of fuel. That does not make it less interesting. If anything, it makes it more interesting because it means we have time. Time to watch the star evolve. Time to catch more ejection events. Time to refine the models, test the predictions, and figure out what actually happens inside a massive star as it inches toward the final collapse. Betelgeuse is a laboratory, a natural experiment running in real time, close enough to observe in extraordinary detail, active enough to produce measurable changes on timescales of months and years rather than millennia. That is rare. Most of the universe moves too slowly for humans to see. Galaxies collide over hundreds of millions of years. Stars form over millions. Even the fastest processes, like supernovae themselves, are over in a few months, and then you are left staring at a cooling remnant that changes imperceptibly over human lifetimes. Betelgeuse is different. It changes fast enough that you can watch it. It is close enough that you can resolve the details, and it is strange enough with its companion and its episodic mass loss and its irregular pulsations that almost everything it does teaches us something new. The broader lessons are what matter most, not when Betelgeuse will explode, but what it tells us about how stars like it live and die, about how binary interactions shape stellar evolution, about how mass loss works in the chaotic outer envelopes of red supergiants, about how convection transports energy and mixes material in ways that the textbooks have always simplified because the real processes are too messy to fit into clean equations, about how the final stages before a supernova actually unfold, not in a smooth, predictable sequence, but in fits and starts, with instabilities and ejections and long periods of apparent calm punctuated by sudden violent events. Betelgeuse is teaching us that massive stars are not predictable. They are not clocks ticking down toward an inevitable end. They are dynamic systems, constantly adjusting, constantly responding to internal and external forces, and their final moments depend on the details of their history in ways that broad strokes models cannot capture. The presence of Siwarha matters, the mass loss rate matters, the rotation matters, the initial mass matters, the metallicity matters. Every variable feeds into the final outcome, and changing any one of them shifts the timeline, alters the brightness of the supernova, changes what kind of remnant gets left behind. That complexity is frustrating if what you want is a clean answer. When will Betelgeuse explode? Sometime in the next few 100,000 years. Not helpful if you are hoping to plan your observing schedule around it. But the complexity is also the point. Stars are not simple. The universe is not simple. The models we build, elegant as they are approximations. They capture the broad trends, the first-order effects, but they miss the details, and sometimes the details matter more than the trends. Betelgeuse is forcing us to pay attention to the details, to build better models that account for binary interactions and episodic mass loss and three-dimensional convection and all the other messy processes that single-star models ignore, to stop assuming that what works for one star works for all stars, to accept that uncertainty is not a failure but a feature, a sign that we are working at the edge of what is knowable, pushing the limits of what our instruments and our theories can tell us. The tools are getting better, the observations are getting sharper, the models are getting more sophisticated. And Betelgeuse, patient and unstable and utterly indifferent to our curiosity, keeps doing what it does, pulsing, shedding mass, spiraling its companion inward, inching toward an explosion that we will probably not see but that someone, someday will. And when it happens, when the core finally runs out of fuel and the collapse begins and the neutrino burst screams outward through space, the observatories will catch it, the detectors will record it, the data will pour in, and for a few brief weeks, the entire astronomical community will drop everything and watch Orion's shoulder tear itself apart, radiating more energy in a month than the Sun will produce in its entire 10-billion-year lifetime. That is the future of Betelgeuse. Not a date, not a countdown, a trajectory. A star moving through the final chapters of its life, close enough that we can read along, strange enough that every page holds a surprise. The Great Dimming was not an ending, it was a preview. A reminder that Betelgeuse is not a static object sitting quietly in the sky, but an active participant in the ongoing drama of stellar evolution. The discovery of Siwarha was not a solution. It was a complication, a new variable in an already complex equation, a sign that the simple story we had been telling ourselves about how red supergiants evolve was missing a crucial chapter. And now, as we look ahead to 2027 and the years beyond, we are not predicting when the star will explode. We are preparing to watch it more closely, to listen more carefully, to learn more deeply. Because Betelgeuse, whether it explodes tomorrow or in 100,000 years, is one of the most valuable objects in the sky. Not because it is dying, because it is still alive, still evolving, still fighting against gravity, still burning fuel, still holding itself together against the crushing weight of its own mass. That fight will end, the core will collapse, the envelope will explode. The light will flood across 700 light-years of space and arrive at Earth, illuminating the night sky in a way no human generation has ever seen, but not yet, not today. For now, Betelgeuse endures, and we, standing at a safe distance with our telescopes and our detectors and our insatiable need to understand, get to watch. That is the privilege, that is the gift, not the explosion itself, but the wait. The slow unfolding of a story that started 10 million years ago and will end, someday, in the most spectacular fireworks display the cosmos has to offer. Until then, we watch, we measure, we learn, and we remember that the universe does not owe us spectacle. What it gives us instead, if we are patient and careful and lucky, is understanding. And for Betelgeuse, that understanding is just beginning. 700 days, That is how long it might take, give or take, for the light from Betelgeuse's final explosion to climb out of the debris and reach its peak brightness. 700 days from core collapse to maximum luminosity, assuming the models are right, assuming the envelope has not been stripped too thin, assuming the companion does not alter the geometry in ways we have not predicted. 700 days. Roughly the length of 2 pulsation cycles, 2 breaths, 2 slow expansions and contractions of a star that has been breathing for 10 million years. We will not see those 700 days, not in our lifetimes, not in the lifetimes of anyone we know or anyone they will know. The timeline has been pushed back, extended by the discovery that Betelgeuse is not alone, that Siwarha has been buying the supergiant time by stripping away its outer layers and reducing the pressure on the core. What looked like an ending in 2019, what felt urgent and immediate and thrilling, turned out to be something else entirely, not the final act, but the middle of a much longer story. A star tearing itself apart slowly, episodically, violently, in ways we are only just beginning to understand. That should be disappointing. It is not, because what we have gained in exchange for the lost spectacle is something rarer. Time to watch, time to learn. Time to figure out how massive stars actually die, not from theory but from observation, not from distant galaxies where the progenitors are unresolved points of light, but from a star close enough that we can map its surface, track its pulsations, measure its companion, listen to the